That's Makerspace. He's the first. Make up for Nice. Enjoy, dude. Breakfast of Champions. Greasy pumpkins. I've been touching high power rocket all week. Flash with it. Just about got enough finished. Make one. Put some grips on that part. And I finally fit lightweight. Oh yeah, that's what you're looking at. That's the original one. That's flyable, but it's got some issues. Yeah, there's all the pieces. 5 pieces enough to get you a flyable model. 5 pieces right there make up a fly. In theory. Nice. And when they start to break, it gets really annoying, doesn't it? Like, really? You're going to do this today? You're going to do that today? And I'm printing out a new motor mounting unit. So this is a 3-engine cluster it's printing out. It literally just finished this like minutes before the stream. Like 15 hours to print. I was going a bit slow, and I did a low layer height to make it pretty. Came out way nicer than I was. Has built-in 1/4-inch launch lugs, also built-in 15 normal rail buttons. I'll probably put 1010 rail buttons on this side, so you know, no matter what pad I go to, I'll have the connection type needed to link up to that pad, all built right into the design. I haven't figured out how to add these little fuel tanks. Phase mode intact, not really nice. Not only does it look good, or thin area, so increases the structural integrity of it. Finally got the threads right. Got all the parts made together correctly. Finally got the nose cone sized correctly. I don't know how I did it, but somehow I made this cone too small. I don't know how I did that. The cone's the right size, but the shoulder's the wrong size. It's a little bit. I had to remake. Because I put so much into making that cone, I'll probably make a small body tube section just to make use of the cone. Nice to throw away, so I'll custom make a body tube off the way. I still have to work on all the shorties. I have the body tube section done for the short one. This requires a CR10 size printer to print. This will print on an Ender 3 size or size printer. If you have a Prusa, Bamboo, just load in Neptune, Stovall, whatever you got, you'll print these. The rocket will be heavier, of course, because you're going to need. But and you can, these are all mateable as well. They'll all join together. Parts are exactly the same. I just made them shorter. Can't scale them. I have to remake the whole model. So in order to scale this, I have to separate this components. I have these components in here with the threading. components up here with the threading, have the cylinder connecting them. Once I separate them, scale the cylinder, and bring the parts back together again, make it whatever size I want. It takes a little work, but that's why I'm just doing 245 millimeters for the small printers, 190 millimeters for the big printer. I haven't figured out the nose cone yet. I can make a shorty nose cone, but I'd rather make a 2-piece nose cone so you end up with a nose size. So I'm going to have to figure out how to cut that cone in half and then thread the 2 parts together. Don't know if I want to use threads simply because that's a lot of work. Make that thread work in that location. A lot of weight. I'll probably do a separate custom thread or a peg configuration where you have 2 mated surfaces, pegs that you glue together, so together you're done. We'll see. This came out. Oh, you guys didn't see it because it'll eventually be public. But I did a well, because first of all, the shorter cone doesn't look as good. Although I will make a short cone for people who want a short. But especially with the short one, you need more mass forward and more aerodynamic length. Shift the center of pressure forward up backwards. With a rocket, have the center of pressure. That's the think of that as the aerodynamic balance point of the model. Then you have the center of gravity, mass balance point. The center of gravity on this tube is right about here. The center of pressure on this tube is probably up here. And that's really bad because that means this is going to tumble through the air. So the longer I make the rocket, the more I shift the center of pressure backwards and the center of gravity forward, and the less mass you have to drop into this nose cone in order to make the rocket stable. Especially since you have this big honking motor mount in the back of the rocket. I might actually make a custom fin unit that does not have a modular motor mount, that just uses 29 millimeter or 38 millimeter, simply because it'll be substantially lighter. This is 1/4 pound right here. No, I'm sorry, over a pound? Might have actually been over a pound. I'll have to look at it. But this part's pretty heavy. Well, it's pretty heavy being at the wrong end of the rocket. It goes at this end of the rocket. That's exactly the part of the rocket where you don't want a lot of, well, that's the wrong one. That's the one that's just a hair too big. That one's the correct size. You're putting all that weight at the wrong end of the rocket. That's making that end of the rocket heavy. The only reason I'm doing this is because I want it to be modular. So, smaller rocket will actually probably have to be heavier and longer than the big rocket, interestingly enough, because 2 of these is going to weigh more than 1 of these. Because every point where you have a coupling, every point where you have an overlap of coupling, you have an increase in mass. Because you have the mass of this section of the rocket and you have the mass of this section of the rocket. That's not going toward moving the seat where it needs to be and the seat where it needs to be. So this rocket will be lighter and more stable than this rocket will. It means you'll probably have to add a whole nother section of this rocket longer in order to shift the seat where you want it to be without having to drop a pound of lead into the nose cone. And then, of course, that means the whole rocket's heavier, which means the whole rocket needs a bigger motor. So ideally, want to print the longer parts. I'm also right now I'm not messing with it just because it's working out so well. But I need to redo the threads. I got these threads from this. So this is that little container. Haze mode print actually. So I got those threads from this. Problem with that is that they're a little bit mass inefficient. So they're a lot bulkier and big. So I want to. Well, probably one of the easiest things I could do is scale the threads up a little bit so that there's not as much meat in here in the 2 dimensions. So get this diameter closer to this diameter. And then also cut the threads in half maybe. I don't need many threads. I also need to reduce the overlap in this mating surface right here. The purpose of that mating surface is to minimize the seam between the two parts. So you get that nice transition. You just have that little tiny seam. Because it's vase mode, I cannot get rid of interface seam. Because in order to get rid of the interface seam, you need a 90-degree shoulder on the bottom part so that the top part can actually touch the bottom part and give you a 0 seam. You can't do that in vase mode. You can't have a 90-degree shoulder in vase mode. So you will always have a point where parts can't close the gap any closer. Best you can do is to have the angle on the top part be as steep as possible, and then you want the angle on this bottom part, so you don't want them to be like this, because you're going to have that point where they hit. You want this bottom one here to be a steeper angle, a shallower angle, so that they can get closer together before the two parts touch. That's how I got this gap. You can see here, this angle is shallow, but inside here, that angle, that gives me a little closer on that overlap gap. Now the good thing about having a large interface that get a nice strong bond. There's no flex. That joint, that's a nice solid joint because it has 3 layers of threading block in place. I make that shorter, tolerances become more critical because this will want to wobble. And it'll also become a break point. The rocket will be more likely to break at that point. So the more they overlap, the stronger they are, but the more plastic it requires and the heavier it is. AKM. Thank you, I appreciate that. So over this past weekend, the NAR, not NRA, the NAR, or National Association of Rocketry, they hold, basically 3 basic national events every year. You have NARM, which actually is in New Mexico this year, so I will be going to that, even if I only go for a day, 3-hour drive away. Go to naramlive.com. You can see I went to 20 years of NARMs, and I have tens of thousands of pictures. Hey, drone shots. And so, NARM is the national sport launch. It's not sport launch, national competition. This year, it's only going to be a 4-day event. It's going to be compressed, but it's 7 days. Sport flying, and you have competition flying. So, parachute duration. Launch a parachute, keep it up in the air as long as possible while still being able to get it back. Sport scale. Make a rocket look as much like a real rocket as you can. Helicopter recovery. Same thing as parachute, but helicopter down and parachuting down. Or streamer down. Or glider recovery. Or egg lofting. And then egg as high as you can without breaking it, or keep an egg in the air as long as you can without breaking it. Competition rocketry. Then you have NSL, or National Sport Launch. It looks like they're trying to do a year now. But they're trying to do an NSL West and an NSL East. Because obviously it'd be much more difficult for me to travel to the East Coast, and it'd be much more difficult for East Coasters to travel out here to Colorado and stuff like that. So looks like the next 3 years, NSL is going to be in Alamosa, Colorado. Means I'll be able to go all years because it's only 3.5-hour drive away. Gotta find somebody who will let me, crash on their, in their room with them, because I can't afford a room. But I'm hoping I'll be flying this at the end of May at NSL. Fun to see this fly. So, the third event is called NARCON, and it's literally a National Association of Rocketry convention. So think of it as like a tech conference for rocketry. Normally it's in person. The last couple of years they've done virtual, and they're probably going to continue to do the virtual one because it allows far more people to attend. So they hold speaker sessions. So you'll have different presenters who will have an hour to present whatever they're going to present to you. They asked me to present one on printing, rocketry. So that actually went over much better than I thought. And one of the issues people had is 3D printing strong enough? So I destroyed one of my parts on live video. And I literally shattered. This one was this one had the incorrect thread size, so it was a part I couldn't use. So I literally took the part like this and compressed it until I crushed it, and I almost failed. I almost couldn't crush it. It was so damn strong. I was like, oh my god, I'm gonna be embarrassed. I'm not gonna be able to crush this thing on camera. Although actually that would be that would either mean the part's really strong or I'm a pussy. But anyway, finally I put it right up against my shoulder and I gave it one last grunt. My face was turning red and the part almost did not give at all. It had PLA, it's brittle. So almost no give until I finally crushed it strong enough and it was like a bomb. It just went bang! And the whole thing crushed. And you can tell it broke across layer lines. Means this part was very, very well made. I knew the part was strong. PLA has the tensile strength of plywood, so I knew the part was pretty. But tall, narrow pipes. Okay, you'll have to show me what you're printing. And also, if you're using a bed slinger, you're probably going to have to slow down a little bit. You're also going to want to increase your temperature and max out your cooling if you're printing with PLA. 210 might be too cold. So you might want to be printing at 215 or 220. Got to make sure that when you put down the next layer, it's hot enough to melt the previous layer and fuse the pieces together. More walls might not be necessary. Okay, more walls increases strength and mass. So, for example, well, and also you have structure. So you have material strength and you have engineered strength. Steven, I'll get to that in a moment. So higher temperature, up to a point, will give you better adhesion. Too high a temperature begins to compromise the plastic itself. So don't go too hot. But too hot is relative to your speed. If you're going faster, then 230 might work. Well, if you were going slower, 230 would destroy the plastic and you'd actually end up with a weaker part. You have to go down to 220 or even 210. Depends on how fast you're going. It also depends on how small a part you're printing. So you said you are printing now 6 centimeters is height. How big is it? Are we talking something 10 sized or 4-inch high power rocket sized? And while you're giving me that answer, Steven, there has been some upgrades. So, for example, I will need to verify this. I believe that the mounting for the CR10, same as for the Ender 3, I think it uses the same carriage. I'll verify that. I know the 2 bolts that hold the hot end are the same. And either way, it uses the same size extrusion rail. So if you have the entire construction, then that should fit on a CR10. Now, the biggest problem you're going to have, and the reason you're not going to find updates for the CR10 is because the CR10 era machines are 12 volts. Ender 3, 24 volts. So anything modern is going to be designed for 24 volts, not 12, which means it's not going to be compatible with your CR10. Now, on the flip side, if we're talking, for example, hot end, then you can simply take your 12-volt thermistor and cartridge that's already on your CR10, transplant those to a new hot end. So there's nothing intrinsically 24-volt about a hot end except for the heater and the thermistor. So as long as you retain your 12-volt thermistor and heater, then, for example, you should be able to put that new direct drive Sprite extruder that Creality came out with on your CR10. I would not put that on a CR10 because it's a single access screw, but the CR10S with the dual screw will hold anything. So you should be able to put that entire carriage assembly on your CR10. The worst case scenario, you might have to drill a hole through the plate if it's missing a hole. But yes, that should work as long as you then. But again, you're going to have to replace your fans, 12-volt fans. You're going to have to use your existing heater cartridge and thermistor because, again, 12 volts. So all of those components won't be usable. They're still good. Hang on to them. They're not going to work with your CR10 because your CR10's 12 volts. Now, you could use the 24-volt fans and put a voltage regulator in line. They're only a couple dollars. They're very cheap. In fact, that's one of the ways we get long-lasting fans. Take high-speed 24-volt fans, and we turn down the power 12 or 14 volts. Makes them just as quiet as a knock to a fan, but they put out more air. So you could do that. You can get voltage converters. They're like this big. They cost like $10 for a dozen of them. Very, very cheap. You hook your input power, you hook a meter to your output power, adjust the pot until you get the 13 volts or 12 volts out of the output, and then you hook it up to your fan. And now no, I'm sorry, that's backwards. That's how you can use 12-volt fans on a 24-volt system that won't let you 24-volt fans on a 12-volt system. You have the opposite problem. Boost the voltage. Be able to do that. I don't know if those little voltage converters can do that. I don't know if I know they can limit the voltage. I don't know if they can boost the voltage. There's enough current there to do it. Fans don't take a lot of current. In fact, as soon as you hit 18, 19 volts, that's probably going to be enough to make those fans spin up just fine. But yeah, you be aware. 12-volt system, 24-volt system. 2 centimeter diameter, so 1 inch. So you're printing a pen. You're printing something very small. Your problem is going to be adhesion to the bed. Your other problem is going to be flow rate. You need to tune your flow rate to be correct. So if you're using a Creality printer, you're going to want your flow rate to either be 94% or 96%. So if you print at a 1-to-1 flow rate, at a 100% or a 1 flow rate, most Creality printers are actually over extruding. The way you test this is this. Now, of course, assumes your printer is functioning correctly. If your printer is not functioning correctly, then this test will give you bullshit results that won't mean anything because it's going to change as your printer changes. But what you do is you download or go into Tinkercad, just make a 20 by 20 millimeter cube. You make it 5 millimeters tall. So literally, I always do this. I try to grab the OBS screen instead of grabbing the actual. Now that I got my dual monitor set up working again. So you literally just come in Tinkercad, grab a little square here. Why is that off? Why? Oh, that's not right. Yeah, that's off. Not be. Scene was off. Oh, that's more like it. If I grab that, it won't. Oh, here. Yes. I was wondering why this. That explains. Okay, so you grab your cube, you drop a cube, you lower it down to 5 millimeters. I'm going to walk you right through this. Right, so you grab yourself a 20 by 20 by 5 millimeter tall cube. Right, and we're going to call that QB. Export QB. Yeah, the audio hum is going to come from the fact that we now have two sets of fans going. We have the PC fans going, and we have the fans in the printer going. You're going to hear a little bit of humming. I do have a cut value in it, so when I'm quiet, sounds go away. But of course, as soon as I start talking and pass the minimum threshold to allow audio to be transmitted, you're then going to hear the fans. Turns on and off. You're going to hear that sometimes and sometimes not. You'll need to take apart the piece, place that fan. It's a little crap fan that's in there. So, whoop. I need to replace that fan, and they're not that noisy, but probably enough for you to, like, when I'm quiet, I can actually see the thrumming. Can't because it's below the cut, but it's there. So now we've extracted QB. Go to downloads. Here. You back over. Move. We're going to drop in QB. Now here's the way we're going to slice QB. Whatever slicer you use, you'll have to use equivalent settings. So I'm using a 0.6 millimeter nozzle, so that's set to 0.6. Yours set to 0.4. But you're going to start off with 0.94. That's used where Creality printers print well. Okay, 6 millimeters retraction, 25 millimeter per second speed, because that's hardware encoded. You can't change that. Change it here, but it's not going to actually change anything. And then do an 8 millimeter wipe. Those are my preferred settings. You adjust these based on what you're doing. If you have a direct drive, probably be 1 millimeter. The layer height 0.2. Then we're going to do 3 top layers, 3 bottom layers, walls. Right? So 3-3-3. It's what I call a 3-3 configuration. 3-3. Infill, we're going to do grid at 25% or 20%. Either one's fine. 20% should be okay. And, oh, I'm sorry. We're going to turn off the bottom layers. So no bottom layer. That's going to help with your elephant's foot and stuff like that. The faster we can get past the elephant foot, the faster we can determine whether you're properly. You can never, ever determine flow rate from your first layers, because your first layers are influenced by both your flow rate and your initial offset. Initial offset isn't correct if, for example, you are squishing a little bit more because you have bed adhesion problems. Well, the software is still going to extract a larger amount of plastic. So that is not a good litmus test for your flow rate. For top layer litmus. So you're going to do a 3-3-3 configuration at a 0.94 flow rate and no bottom layers. So not 3-3, but the basic 3. So here's what we're going to print. See, we have our 20% infill, and I believe let's go to 25%. 25% does work better for this. And then we also have to adjust your overlap. So that is going to be here, outline overlap. You'll have a similar setting in Prusa, Cura, Idea Maker, but I have it currently set to 30%. After we adjust the top layers, I'll then tell you how to adjust your outline overlap. So there's your print. So your first layer doesn't matter. We don't care about the first layer. We don't care about the walls. We don't care about any of this. The only thing we care about, final top layer. Now, when you look at this final top layer, physically in person, you're going to just see 2 points of either under or over extrusion. You're going to see individual layer lines. And what you're going to do, we're going to you think of this as your individual layer lines, and there's potentially going to be a small gap between the lines that it draws. If you are under extruding, you'll have a gap. You can actually maybe stick your fingernail in, probably be able to see it. Right? So what you need to do is just wherever your flow rate is, print this. Then go down to 0.98, print it again. Down to 0.96, again. Down to 0.94, again, down to 0.92. Again, what you're looking for is you're looking to intentionally create gaps between the lines, between lines here. All right? At whatever point you see a gap, go back the other way by 1. So let's say I get down to 0.92 and I see a gap. Well, now I'm going to bump it up to 0.93 and try it again. Do I still see a gap? If I do, bump it up to 0.94. You bump it up until the gap goes away. Exactly enough for the gap to go away. You're going to notice it looks like ironing. That surface layer is going to look shockingly smooth. Hey, red light. That top layer is going to look shockingly smooth when you nail it. And when you nail it, that's where you stop. You leave your flow right there. Mine Creality printers tend to be happy at 0.94, 0.96. This will change with filament. So if the filament you have today is, 1.78 millimeters instead of 1.75 millimeters, you might have to go down to 0.94. If your filament today is 1.73 millimeters instead of 1.75 millimeters, you might have to bump it up to 0.96. So if it's a critical project, if it's a non-critical project, you don't really have to worry about it. Once you get the right number, that's close enough for government work. If it's a mission critical part, then you might want to do the little QB again. And because it only takes a few minutes. This only takes looks like it's a 7-minute print. It's going to take you longer to heat up than it is to print the part. All right, so spend your 15 minutes, do your QB like I just showed you here, and adjust. Eventually, you won't even have to do repeat prints. You'll do your, like, say for example, you decide on 0.94. That gives you the best quality. You'll print your QB and you'll just look at it and go, okay, I need to go up a little or down a little. You won't even have to do a retest unless it's like grotesquely off. You'll just look at it and go, yep, let's go down a little bit, let's go up a little bit, or it's good enough. But that gets you your flow rate. Now you also need to adjust your overlap. Now to adjust the overlap, you have to look at this part here. Hey John, you have to look at where the green lines intersect the first of your 3 perimeters. You do need an overlap. You can't have no overlap because otherwise the parts might not adhere together. You need that line, that here's your wall and here's your infill, your top layer. You need that to overlap a little bit. Otherwise you won't get adhesion, you won't get a strong bond between the parts. So you want a little bit of squish there. But if you look at it closely, you'll notice it looks like little curly cues, like little swirls, where every one of those lines touches the wall. And those swirls become more pronounced, like a puff pastry, because you have too much overlap. Well, then you put it down. So if 30% is too much, try 25%. No, I wouldn't go below 20, unless you have a mechanical reason. So then after you adjust your flow rate, because you can't adjust your overlap until you adjust the flow rate, because the flow rate influences the overlap result. The result's going to look different. That's also why you can't use this first layer. You can't use the elephant's foot to determine anything. That elephant's foot is meaningless until after you've adjusted flow rate and after you've adjusted your perimeter overlap. So once you have your flow rate so that top layer looks nice, nice and flat and smooth, you should be able to touch it and barely feel those layer lines. Feel almost like glass when you nail it. You'll be able to see the lines, but you'll barely be able to feel them, and won't be any gap for you to stick your fingernail in. Then you adjust your overlap. You get that looking right. You might have to accept a little bit overlap in order to make sure you get a good bond. You'll also notice if you're under extruding that your walls, the 3 walls, they won't touch. There'll actually be a gap. That's usually a mechanical problem. That usually means there's a clog or restriction in your hot end, or a bad sized filament, or a loosening drive gear on the feed motor. That's usually a lot more than just flow rate. But that's how you adjust your flow rate. That's how you adjust your overlap. Then after you do those 2 things, cannot change those things again, because we now know those things are correct. So we leave those things alone. Now you adjust your first layer settings. I would not adjust your squish, because you know the squish you got works, right? It's the part sticking, so leave that alone. What you do is compensate for that. So, for example, if you're noticing that you have a big elephant's foot, well, the slicer has settings for the first layer. So there's a whole section here for first layer settings. So adjust those. You know, for example, you notice right here, I got 10 millimeters per second for my first layer speed, because you want that first layer to go down. Want it to go down slow, hot, and sticky. You want to make sure it sticks to that bed. And then you can adjust layer height. I wouldn't adjust that very much, because that's the same thing as adjusting the screws on the bed. You're going to change your squish, and you might lose your bed adhesion. Instead, modify your first layer width. If you have a little bit too much of elephant's foot, tell your first layer width to be 0.35 or even 0.3. It'll extrude a little bit less plastic. If you lose adhesion, don't adjust the bed. Slow down. Raise the temperature. Drop the speed. Give that plastic a chance to fall, touch, and stick to the bed. Why is this important for his? Let's get back to talking about 20 minutes ago. Why that's important for his pen that he's trying to print, or whatever he's trying to print, his 2 centimeter tiny thing. Well, because your first layer is critical. Because, you know, when you're trying on like an Ender 2, I can actually print a pen where that little point right there is the only thing attaching it to the bed. It will stay. There are some rules, because you're moving the bed. It means that pen is moving back and forth. Now, there's not a whole lot of mass there. Centimeter by 6 centimeter. Not a lot of plastic. Don't really have to worry about mass. Don't want is the bed going that pen is going to create a resonance. It's going to start to resonate at the frequency that bed's moving back and forth. It's going to vibrate and move. And what's going to happen is the pen is going to move relative to the nozzle, and then the nozzle is going to collide apart. When the nozzle collides with this, at most you might hear a clink as it pushes the plastic out of the way. But when you're printing something like this, it knocks it right off the bed. Okay, so that's where flow rate comes in. You're extruding too much plastic. That means that plastic is going to be thicker than the machine code expects it to be. Remember, these printers are dumb, deaf, blind. They have no sense of touch. That you could put a blob of coal on that bed and the printer will try to print straight through it because it has no idea anything is there. All it understands is, you told me to turn this motor this many turns. That's it. That is the only thing your printer understands. Turn motor 4 turns. Turn motor 7 turns. Turn motor 12 turns. Turn motor 147 turns. That is all your printer understands. The fact that turning this motor moves the plastic that way means nothing to the printer. The fact that turn this motor moves the print head on the y-axis 15 millimeters means nothing to the printer. Your printer only understands turn motor, turn motor, turn motor, turn motor, turn motor. And those are your kinematics. Number of turns, and juggling all those turns together in your pathing code is what creates the motion on your printer. So you have to be the brains and the intelligence of that operation. So if I tell the printer to turn the 4 motors on my machine in such and such an order, and set the electrical current for the thermistor and the heater to this and the fan to this, it results in that. Right? That's what you end up with. But that's not what you end up with. That's what you end up with if nothing goes wrong. If something goes wrong, your printer has no idea. It's just going to then continue on and do the second layer and have no idea that first layer succeeded or not. It's just going to do it anyway. Well, here's the problem. The programming you gave it told it to extrude this 0.2 millimeter tall by 0.4 millimeter wide by 20 millimeter long path, basically turn the motors this many times, and the result is you get a line of plastic that big. Well, when the slicer then says, okay, now I wish to print the second layer of the slice. Boom, there's layer 2 of the slice. Well, the problem is that layer 2 is floating in midair. It doesn't exist anywhere. Nothing underneath it, unless the first layer succeeded. Okay? Now, what happens if I... See how on here, this layer is thicker than this layer? That has to do with your flow rate settings in the slicer here. But point is, this actually happens in real life. If the software said, I'm going to extrude a 0.4 millimeter wide by 0.2 millimeter tall layer, what happens if I extrude too much? What happens if this layer is 0.3 millimeters tall? Because I extruded too much plastic. Well, you're going to get a snowplow effect. You know, the plastic, instead of having this nice layer coming out of the plastic, it's going to extrude out like this. It's going to look a lot like this. So in here is the 0.4 by 0.2 millimeter layer you intended to print, and here is the excess plastic that came out of the nozzle. And what's going to happen is the excess plastic is going to go around the outside of the nozzle, and the nozzle is going to push it out of the way. You can actually see this when you do your infill. And sometimes you can even hear it. You hear it go as the nozzle hits each cross layer of the plastic as it goes back and forth, creating its pattern. If you hear that sound, you're extruding too much plastic. Because what's happened is, total to extrude a 0.2 millimeter thick layer, it then lifted the carriage up 0.2 millimeters to 0.4 millimeters. This, of course, assumes your kinematics are functioning correctly. Remember, your printer is not capable of lifting the nozzle 0.2 millimeters. That's not what it does. It turns the Z-axis stepper motor X number of turns. And if you, or the manufacturer, program the software correctly, and if the hardware is working correctly, and if nothing is interfering with the hardware, like a bent shaft, or then X number of turns of that stepper motor will result in a 0.2 millimeter lift of the head. So we're assuming that. But if that first layer has too much plastic, then what's going to happen is I put down this much plastic, and then I come down on top of it, and I put down this much plastic over top of it. Perfect, right? What happens if I put down too much? Well, now my nozzle's crashing into that too much plastic that's there. And it's going to melt and push it out of the way, and you end up with that sloppy first layer snowplow effect, and all those lines and stuff like that. Well, the problem is, if the force of your nozzle hitting that plastic is strong enough, it can actually pull the first layer off the bed. And now you're going to have a weaker bond to the bed. This can manifest in, for example, printing a square and your corner curls up, right? Or it could manifest in the entire cylinder you're printing falling off, right? And that's what's likely happening with his. Now, there are many different ways to adjust this. First, you're going to do, you're going to download QB. You're going to go into Tinkercad. You're going to make a 20 by 20 by 5 millimeter cube, and you're going to download that. You're going to print it with 333. Start off at 1.0, 0.4, 0.4, 0.2 millimeter layer height, 25% grid, not rectilinear infill, and then you're going to tell it no bottom layers. It's going to make your life easier if you get rid of bottom layers. If you want to print bottom layers, make it 10 millimeters tall, not 5 millimeters. You need to be far enough up that the elephant's foot has averaged out of the equation. That requires about 5 to 8 layers. So you need to make sure it's tall enough that the elephant's foot is no longer influencing the current layers being printed. And then you adjust your flow rate until you get that perfect top. Then you adjust your perimeter overlap until you're satisfied. Got a good solid merger, but not too much, dollops of icing, creating that little dollop pattern on the outside edge. Once you have that adjusted, and then once you've adjusted your first layer width, leave the height alone, and everything else, just adjust the width. Like if you have a big elephant's foot, decrease the width of the first layer. So your nozzle's in the same place, just putting out a little bit less plastic. If you lose bed stiction, then what you're going to do is not adjust the bed because you know that works. You got a part to stick, okay? Leave it alone. Instead, slow down and print hotter. So in my settings here, see my first layer runs at 10 millimeters per second, even though my speed is set at 50 millimeters per second. And I'm actually going to lower that to 5 millimeters per second because lately I've been lowering the print speed to 10 for the first layer. So I could just do that in here and I won't have to keep putzing with it on the printer. And then under temperature, you notice I have two settings here. I have first layer, 220. Then I have second layer, 215. Now, 215 just happens to be the right temperature for my vase mode print. For my normal printing, I usually drop down to 210. So what I'll do is I'll make the second layer 210 and the third layer 215. The third layer 210. And then the third layer is when the fan turns on. So for the first two layers, no fan. So layer 1, 0 fan speed. Layer 3, 100% fan speed. And then temperature, I crank it all the way up to 220. And I lower the speed all the way down to 5 millimeters per second. Slow, hot, sticky. Okay, the slower, the hotter, and the stickier you make that first layer, better it's going to stick to the bed. Now, if you're printing a lot of tall, skinny parts, two things upgrade you're going to want to make. First, you want a flex plate. Nobody should be printing on anything but a flex plate anymore. It is so ridiculously awesome that the very idea of printing on anything but a flex plate is crazy to me. So flex plate, I can't take it off the printer because I'm actually have one. So yeah, even if it means putting it on top of the glass and making it heavier, I don't care. I want a flex plate. Second thing is, when you have a flex plate, you can buy multiple flex plates. You can buy extra pieces of steel. So a flex plate is made of 3 components. You have the magnet, which got sticky tape on it. That goes on your print bed. You have the steel plate, which magnetically adheres to the magnet that you put on the print bed. And then you have your printing surface. Another sticker. That goes on the steel plate. So your steel plate is a sandwich of a sticker and steel plate. Then you put the magnet on the print bed. Wham Bam, T3DP, bunch of vendors on Amazon. If you're printing high temperatures, like if you're putting your bed to 100 degrees Celsius regularly, you're just printing PLA Petchy, don't worry about this. If you're doing ABS, ASA, nylon, polycarbonate, and you're hitting 100+ degree bed temperatures, stick with somebody like Wham Bam or TH3D, because they are, magnets have something that's called a Curry temperature. Heat destroys magnetism. If you make a magnet hot enough, it stops being a magnet, and it doesn't get it back when you put it down. Damage is permanent. Yes, Wham Bam costs a bit more money, but they are top notch. Nice thick magnets, the proper 3M adhesive, nice clean edge steel plates with tabs. So there's no way you're pulling that plate off of there accidentally. They stick good. Like I have a Wham Bam plate on my Ender 5, but I don't have the Wham Bam magnet on the Ender 5 because it already came with a magnet. The difference between the Creality magnet and the Wham Bam magnet, it's like flop, flop, snick, snick. it grabs, big difference. But why print good enough and I didn't feel like peeling it off. Wow, for the whole kit? Now keep in mind, they also sell just the magnet, just the plates, stuff like that. But they may have gotten the shipping issue taken care of too, because a lot of their price was shipping. But TH3D is also pretty good. He makes his sheets are pretty decent. But the problem when you go to higher temperatures is that magnets have different Curry temperature. So higher quality magnets have a higher Curry temperature, meaning they can get hotter without losing their magnetism. And I know the TH3D ones are good. I know the Wham Bam ones are good. Cheap ones you get off of audio. Audio looks pretty good. Well, I am pretty far away. Bring the mic closer. Is that better? Yeah, I see it spiking a little bit better. Let me turn this up a little bit. Testing, testing, testing. Let me get into the yellow. me jack up a little. Yeah, I should be more in the yellows here. How's that? There we go. Now I'm just touching the yellow. Does that sound better? Does it sound better now? Is the volume better now? Okay. I boosted the gains a little bit so we get a little more peak out of the audio and brought the microphone closer, which of course will help a lot. Normally I'm sitting up here. Now I'm back here, so I brought the microphone forward. So the higher Curie temperature of the Wham Bam and TS3D magnets, meaning they won't lose their magnetism when you start cranking your bed to 100, 110, 120 Celsius for the higher temperature plastics. That's important to remember. Now, the advantage of a mag plate is that you can put a different skin on that plate. So do you remember the original Ender 2, Ender 3 print beds? How we called them fake tack because they were copies of build tack, although not really. Build tack is a very smooth surface, but it's not PEI. While the original Creality beds were soft, they were almost like fabric. They had a fabric-like feel to them. They weren't. They were hard, some form of polycarbonate, but they were they had a texture to them. It was almost like a cotton-like texture. That's what you want. If you're printing tall, skinny stuff, want to get a sheet of that cloth-like, textured-like plastic skin to put on one of your mag sheets. I don't advise double-siding a mag sheet. In theory, you could put one skin on one side and one skin on the other side, and then you could flip the magnet over. But I've noticed that those sheets tend to prefer one way over the other. Most of those metal sheets have a little bit of a bow to them, and you want to make sure that bow is down, because otherwise, thank you very much, Michael. I appreciate that. You want to make sure that bow is this way so that it sits on the bed like this. If it sits on the bed like this, the sides could peel up while it's printing a large part, and you don't want that. Also, when you increase the distance between the steel and the magnet surface, you increase the magnetic strength, so you don't want to do that either. Buy another steel plate. Have a different steel plate based on whatever you're printing. So you have one with PEI, you can have one with polycarbonate, you can have one with the fabric surface. And this way you can use whatever plate makes the most sense based on what you're printing. But those fabric-like surfaces are a lot better for really gripping the part. Meaning when you lay down that first layer, it tends to stay put. That will help printing tall things, tall skinny things. Now something like this, I don't have a problem with because it's so big. When you start getting skinnier and skinnier and skinnier, your what we in the industry in Rocketry we call it a moment arm. So think of it like leverage when you use a pry bar. So if I take a screwdriver and I stick it inside of a wedge and I use that screwdriver as a pry bar or something, well, if I make that screwdriver this long, I get a lot more pry force out of it. So you want to your long pen is a long pry bar, meaning the taller you make that pen, the less force it takes to actually tip it over and break that bond with the bed. But the big problem is going to come with your flow rate. If your flow rate is too high, you're going to print a layer, and then when you go up to print the next layer, you're not going up enough because you extruded too much plastic. And each time you go around, you're colliding with that previous layer of plastic. And little by little, you're breaking the bond, the bed. And eventually, it's going to pop off. You have such a small... Now, you could add a brim, even a 2-layer brim. You can make your skirt like 15 perimeters and 0 distance, and then make it 2 layers. So in here, that would be this here. So I would set my skirt offset to 0, my skirt outlines to 10 or 12 or 15, and then maybe even make my skirt layers 2. And so let me show you what that'll do. So let's go 0 for that. So 15 for this. that's going to give you this. If we go down to the first layer, what you see is this. So the blue and the orange is your actual part. So the dark blue is your outer wall, light blue is your inner walls, the orange is your infill, and the purple is your brim. That's what's going to separate. If you have a hard time separating your brim and you don't want to change your squish settings, you can compensate for that by changing your offset. So for example, I can make the offset 0.2 millimeters. It'll probably still touch, but it won't touch quite as solidly. So your brim will come off easier. Or just use a deburring tool to take it off. Now what I could do is I could make that brim layers. And then you get this. You see I changed it to 0.2. So now there's a little gap between the brim and the part. Because of squish, that gap will probably end up being 0. And now I have that. Yeah, there it is. Okay. See, now I have 2 layers of brim to remove. That'll give me a much more solid base. This doesn't need it, but if you have if you're printing ABS or ASA and you're printing a large box, you keep getting peeling, this will help. You probably won't need 2 layers. 1 will probably be enough. If you're printing your little cylinder, 2 layers might be the difference between sticking and not sticking. But still, adjust your flow rate, adjust your overlap, get that all done right, and you'll probably notice you'll stop knocking over parts. Also, don't go too fast. Also, try to now that's all everything I've talked to you about so far is slicing changes. So we've changed the mechanical properties of what we're doing. You can also engineer a solution. So, for example, increasing your wipe much longer might help, because what'll happen is when it's done printing a perimeter, let's say I tell it to you're printing a little tiny pen, so let's say I do 12 millimeters of wipe. That might result in plastic, 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 no more plastic. If I've stopped extruding now, I'm going to keep moving over top of the part. What I'm doing is I'm smoothing down the layer of the part. Now, that could have negative consequences elsewhere, but that little bit of smoothing might be enough to allow you to print the part without it knocking itself over. You're also going to want to adjust your retraction, how much retraction, and your wipe, because you can create what's called a booger. So if I turn on my markers here, now these are things that the slicer is adding. So here's where the tool head is. That's where it ends up. Red lines are travel movement. That's where the tool head has moved, but it's not extruding any plastic. Where the colors are is where it's moving and extruding plastic. Red lines is where it's just extruding. It's moving but not extruding. So if we go down a couple layers, we can actually see that. So we can see when it finishes printing this outer perimeter, it then moves here, and then it moves here, and then it begins to print the infill. That little blob is actually more indicative than you might think. So can anybody tell me what that right there is going to be on the model? If you've done a few prints, you know what that is. That's going to be hard to find on mine, but it's there. That's your zit line. That's the line going up the outside of the model. Mine are less pronounced because it's a vase mode print, which is not really going to have, actually the gray one will probably be more visible. Yeah, there it is. Now the reason that's so pronounced on my model, because that's not a layer transition. That's actually a cut going through the model to the inside. That's what allows me to vase mode a model with 2 separate walls, still be vase mode. I have to connect this outside surface with this inside surface in order to vase mode print. And so that connection is actually a slice going right through the model. So there's actually a gap between this half and this half, but they're so close together, the plastic is fused. But there's actually a line there, and that's why it bulges a little. I have to make sure it fuses. So when I do these prints, I actually print at 1.0 with flow rate. I intentionally over extrude just a tiny bit to make certain all these parts actually touch. Because, for example, I have ribs connecting the inside and the outside wall together. They don't cut, but they touch. And I have to make sure they fuse. So, teeny bit of over extruding to make sure they fuse. You can actually see all those individual cuts on the outside. Because on that part there, I do it on the outside. While on this part here, I do it on the inside. There's technical reasons for that. But each point where the printer stops and then retracts the filament from the hot end and then begins either the wipe or the move operation to move somewhere else, it creates a blob so I can see here where it's happening on the print. And if you were to print that cube, you will notice that zit line exists right there where it shows you it on the slicer. So that zit line is a problem though, because if your printer is not properly retracting, if your ooze control isn't functioning properly or as you intended, you could actually end up with a little blob right there. Now on a part like this, if it had a blob, it wouldn't matter, because this part's got a big enough base that that little tiny bit of plastic is not going to cause a problem. But on your pen, that's 2 centimeters in diameter, it's less than an inch is 25.4 millimeters, so you're looking at like 3/4 of an inch. That's small enough that that little blob, when your nozzle crashes into it on the next layer, that could be enough to knock your print off. So you're also going to have to play around with your flow control and your ooze control settings. This is going to be different depending on what slicer you use, but it all comes down to the same thing. Everything that we just did, all the settings that we just did for your infill, your flow rate, for your overlap, well, guess what that's going to do? That's going to make your zit line better, because everything we did to change those also improves your zit line. So you're going to, when you sit down and you print that little cube and you get your settings tuned just right, you're going to go, hey, the zits aren't as bad. That's because you're extruding the correct amount of plastic. So when you retract, it doesn't have to do as much work because you're not putting out all this extra plastic. You might still have zits though, and there are ways around that. So the way I handle that is I've 4 to 6 millimeters is usually enough for a Bowden printer. And I use something called wipe. Wipe basically means I want to print from here to here, and then I want to lift up and do the next layer. Well, instead of going stop, retract, lift up, and then start printing the next layer, instead I'm going to go stop oozing, stop extracting filament, begin retracting filament, and as I'm retracting filament, keep moving. And this way, if a little bit of extra plastic comes out, it's being pushed into the layer that's already there. So it's less likely to create a blobby zit and more likely to create a streak. It's going to be less noticeable. Then there's also settings here. I believe it's not under layers. Where is it? There is a setting. Well, infill telegraphing to the outside. I'm going to show you how to fix that. That's because Cura is stupid. Stop using Cura. That's this right here. This section right here is defaulted in Cura to be backwards to what reality should be. Okay? So, when I print this, what prints first? Forget about the purple. You have the blue outer wall, the light blue inner walls, and you have the orange infill. What prints first? Well, obviously you want to build the container first and then fill it in, right? Well, no. Cura defaults to the opposite. Cura prints the orange infill first and then prints the outer walls. Well, the problem is you're printing with a thermoplastic. So you're melting a plastic, extruding it in a semi-viscous liquid state, in a viscous semi-liquid state, and then you're zapping it with the cooling fan to harden it back into a solid. Well, if you print the infill first, and the infill is a little bit too large, and then the infill solidifies into a solid, well, guess what happens when you print your outer wall? It's literally going to push the outer wall out. Because here's my infill, and I come and do my outer wall, and the infill's in the way. Well, guess what happens? My outer wall goes boop. Now, it partially melts it, but it also pushes some of it out. And that's why you're seeing the infill telegraphed to the outside of the model, even with free perimeters. Because it's literally pushing it out of the way. Never, 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 never. Always print walls first, then infill. So in your settings, somewhere in Cura, you'll have to do the little search thing in Cura. There is going to be, is it here? This is going to, your printing order is going to be somewhere. So I always print inside out. Now, there are times where outside in makes sense, but you also want to make sure you do not print the infill before the perimeters. You want to print the perimeters and then the infill, or the walls, then the infill. So you have two settings. You have the order in which you print the walls, and you have the whether you print the walls or the infill first. You want to print the walls first, then you want to print the infill second. Also, in most cases, not all cases, but in most cases, you want to print inside out. Because sometimes when you start printing a layer, the plastic is not exactly correct yet. And you'll notice there's a little gap there where it for like a millimeter, it didn't extrude plastic because it oozed somewhere, got caught somewhere, whatever. Point is, you don't want that ugly mark on the outside of your model. You want to hide that on the inside of your model. So you want to do inside out, so that by the time it gets to the outside wall, the filament is flowing nice and smooth and regular and regulated. It's doing what it's supposed to be doing, and you get that nice, clean outer wall. But yeah, you want to, most of the time, you want to print inside out. There are times where you might want to print outside in, depending on the part you're printing. If you are printing a part with interior space, and you notice a lot of angel hair inside the part, like you see those strands, like spiderweb strands all over the not filament, not attached. I'm not talking about like blatant failed print. I'm talking about little hairs on the inside of the model. Usually happens when you have a wall that is getting smaller like this, right? In that case, you might want to switch to outside in, because what's happening is you have your three layers like this, your three walls, and you print three more walls on top of those walls, right? Now that's all fine and dandy, right? Looks just like that, no problems, right? But what happens when you print an angled wall? Well, what you get looks like this, because you're printing at an angle, so it's a stair step. And if you print the inside first, there's nothing for it to stick to. All right, so in that case, you might want to make sure you print this wall first to make sure that this wall sticks, and this wall has something to stick to, and this wall has something to stick to. So there are times where you might want to change the order that it prints the walls, but in most cases, inside out is what you want. But I can't think of a single instance where it makes sense to print the infill first. I cannot come up with a single instance where that makes sense. But there probably is. 3D printing has unlimited potential, but I have yet to encounter a situation in my tens of thousands of hours of printing where it ever made sense to print the infill first. You print the walls first because that defines the shape of your object. So if you're going to have plastic pushing plastic out of the way, you want the wall pushing the infill out of the way. not the infill pushing your wall out of the way, which is going to distort the outer shape of your object, and you'll get telegraphing of the infill on the outside of the model. So that's now, of course, adjusting these settings, your flow rate and your overlap is going to reduce that telegraphing. So that will get better as well. But you can just fix that outright by doing walls first, then infill. And unless you have a specific reason not to, you should typically do 3 walls. Okay? So the first wall handles your overlap with your infill. The second wall stabilizes everything between the first wall and the outer wall. And your outer wall should then be your most stable and cleanest extrusion so that you get that nice, clean outer exterior. Okay, what else do we have here? Steven also asked about Noctua fans. I wouldn't bother with Noctua fans. I mean, they are nice. They're good fans, but okay, for hot end cooling, you're probably okay. For interior cooling, you're probably okay. But there's a way to get 95% the quiet of a Noctua fan without paying any more money. And that's you buy dual ball bearing fans. The reason these fans are noisy is not because of the air they're moving. These are not high-speed, high-flow fans. You know, you turn on a leaf blower, that's a high-volume, high-speed, high-flow fan. You're never going to quiet that. There's nothing you can do to make that quiet. That is the nature of moving that much air. These are not high-flow, high-speed fans. These are low-pressure fans, not high-pressure fans. So the fan isn't making any noise, or very, very little. The noise is the interface between the fan and the motor driving it, the bearing. That's what's making the noise. The noise you're hearing from my computer is the cheap piece of shit fan that has a hydraulic bushing bearing that's either losing oil or it's not made right, and that bushing is literally going on top of the bushing, but it's doing it at 5,000 RPM. And that's what you're hearing. You know, at low speed, it's going to be a click, 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 click. But when you start doing 5,000 RPM or 2,000 RPM, that turns into a, because of how fast it's happening. So when you go online, you got to know what fan you're looking for. So, for example, an Ender 3 hot end fan is a 40-40-10. That means it's 40 millimeters on X, 40 millimeters on Y, and 10 millimeters thick. That's your Ender 3 hot end cooling fan, not your parts cooling fan. Your parts cooling fan is usually a 40-40-10 blower. So the difference is that's your standard fan, while the blower is going to be a block with an opening here and a vent here. So one is an axial fan, the air is just passing through, while the other one going like that, and it's coming out the hole in the bottom. That's a blower. So your standard cooling fan is 40-40-10. So what I do a search for is I do a search for 40 millimeter, that's the size of the fan, 24V, and be careful because Amazon is going to stick 12-volt fans in your search results even though you asked 24-volt. So be aware of that. I do a search 40 millimeter, 24V, dual bearing. That's it. It's usually going to be from a company called Win or Winsin. There's a couple others, but you want it'll say dual ball bearing fan. If it doesn't say dual ball bearing, it's a bushing. It's going to eventually stop being quiet and it's going to be noisy. If you get a dual ball bearing fan, which is only like $1 or $2 more than the regular bushing fans, it's like almost no price increase. In fact, I'll show you. So literally, I do a search for 40 millimeter, 24-volt, dual bearing. See? 40-10, that's the size of the fan, 40 millimeters by 10 millimeters. It's 24 volts. Hey, Starnest. And then here, dual ball bearing. This one even says works with Ender 3, but you get the point. So that looks like a pack of 2 for like 11 or 12 bucks. Here's another one. Dual ball bearing, 11 bucks for 2 of them. And here's your blower. See here? This is a fan, and this is a blower. This one even comes with the little ducks. Thank you, Starnest. So if you wanted to upgrade your fan, now if you have a big blower, that would be this one. This is a 4020. This is a 4010. So these 2 fans right here, that's what's on your Ender 3. That's what's on your any typical Creality 24-volt printer is going to have this. Now your older Ender 2 or CR10 is going to have the exact same fans, but in 12-volt versions. But you buy one of these, you buy one of these, and they will be just as quiet as a Noctua fan for 1/5 the price. And if you want to make the fan even quieter, slow it down. The only fan you don't want to slow down is this one. No matter how much noise it makes, you need this fan to put out as much air as you can. You do not want to replace this fan with a slower fan. You need the flow. You need to move the volume of air in order to cool the part. Most of these other fans can usually get away with a little less flow. You might have to increase your maintenance routine. So you might have to go in there with a duster every now and then and blow off the dust off the hot end so that the fan can do its job better. Just like your ceiling fans and your mini splits, you got to clean off the filters, you got to clean off the fan blades, or they don't blow as much air. Same thing applies here. And because you're using a slower fan, you're getting less airflow. Hey, Mike. We're talking about high-power rocket parts and answering people's questions on, how to for your 3D printer. So, you could take this here and, let's see. 12-volt regulator. Let's see if I can find it. Okay, what we want is the itty-bitty ones. Like this kind of thing. So we're going to do 24-volt buck. Let's see if that gets us what we want. There we go. This is way bigger than you need. You don't need that. But you can see even these complicated ones with an LCD screen, they're dirt cheap. But they make itty bitty ones. They're so tiny, it's ridiculous. They actually come as a sheet, and you got to break them off. Here we go. Here we go. There you go. That's what I'm talking about right there. So 14 bucks gets you a dozen of them. You'll never need any ever again. They're about $1 a piece. So these have an input and an output, and there's a little adjustment pot right there. So you can see here, one side is the input, one side is the output, and then you have that little pot right there. What you do is you connect your 12 volts to the input side, you take your voltage meter, and you plug it into the output, and you're going to get a reading. Then you have to plug this into your printer, by the way. You can't plug this into your own power supply because you might get a different result. And then what you do is you adjust this pot until the output is 12 volts. And now you can run your 24-volt fan at 12 volts. You cannot do this for the blower fan because that fan is PWM controlled, meaning you're using pulse width modulation to adjust the speed of that fan. You cannot use it on that fan, but you can use it on all of your steady state fans. That's your hot end fan. That's the fans inside your brain box. Basically any fan that just turns on and runs. Doesn't change speeds. You can plug one of these into it, so you can use a ball bearing fan, and then you can take one of these and turn down the power a tiny bit. So maybe you don't go all the way down to 12 volts. Maybe you run it at 16 volts or 18 volts or 20 volts. Point is, you're slowing the fan down, which means you're going to make less noise. So with a little bit of tiny extra work here, by installing one of these, you can install a ball bearing fan that's already going to be almost as quiet, and then turn it down a tiny bit, and now you are silent. And it costs you, $5 instead of $40. So let me show you the difference here. This is going to blow your mind. And I have links to all of these in my Amazon links page. If you go to my Amazon link page and you go to 3D printing, parts, tools, and accessories, you'll find all of this in there. Oop, we didn't go back far enough. There we go. So for $5.50, I can get 2 of these fans, or I could pay $15 for one of these fans. $14. So here's your 3-pin 4010. So 3 times the price for a fan that's not going to blow as much air. All right, or I can get 2 of them for $11 and then pay $1 for the buck converter. And you could probably actually, this alone without the buck converter will probably be quiet enough to make you happy. But if you want that little bit of extra quiet, that'll get you there for a fraction of the price and for a much longer lifespan. I mean, these fans will basically last forever. You're very unlikely to ever kill one. Also, there's another company that makes quiet fans. If you really do want the quiet fans, let's just do a search for quiet and then it'll come up. Let's see. They might be on. Oh, here it is. Noise Blocker. There it is. Noise Blocker is the other company. So Noctua is the one company, and Noise Blocker is the other company. So here's the Noise Blocker 40-40-10. It's $12, while the Noctua 40-40-10 is $14. About the same price. Stay away from the RGB crap. It's not worth it. Not like you're gonna sit there watching your 70-hour print and go, oh, pretty colors. Who cares? Just get cheap and good. Just get the ball bearing fans good. Just make sure it says dual ball bearing. If it doesn't say dual ball bearing, walk away. Also, make sure it actually is 24 volts. I have had Amazon show me 12-volt fans, and I open up the package and it's 12 volt. What the fuck? They sent me a 12? Oh, I ordered a 12-volt fan, but I searched for 24 volts, so double check that. What was your biggest print you had? I have two I have 2 figures that I printed out. Sorceress and Naomi Wu. They're both almost 6 feet tall. So they're about 4 pieces printed on my Chiron that I then glued together with a 1.2 millimeter nozzle. This is going to be one of my biggest prints as well, because let's show you the rocket. And what we're printing, that's what we've been thinking over, right? So last week you saw me design this, and I printed it out. Let's go full screen for this. You guys are gonna love this. So here is the fin can. So the launch lugs are built in, threading is built in, top and bottom, fins are built in. It's all ready to go. And I also made a modular motor mount, very heavy, but it's modular. So this is a 29 millimeter motor mount, and it just threads right into the bottom here. There you go. Now I have my 29 millimeter motor mount. The only glue you need for this is to glue the paper tube into here. That's the only time you'll ever need glue for this. But here's the cool part. These are all interchangeable. So I designed a different fin. You notice this one, fins are a little wavy. They're a little squishy. All right, so I made some improvements to that. I also knocked over 150 grams off. I made a 3-fin unit that actually has these cool little drop-off tank things. They don't drop off, but they look like it. Extra fins. And not only does this look cooler, but it's 150 grams lighter. This only weighs 400 grams. I have dual reinforcements here, line there, plus the tank shape, nice and stiff. This one has rail button and 1/4-inch launch lug. And of course, it's all modular, so all these parts fit together. I also got the body tube segment. That thread's on there, locks in place. That's not going anywhere. Then you also, I can print more of these segments and keep stacking them as high as I want within reason. You also have the nose cone segment. Let's thread it on the bottom, sleeve on the top. That goes on this part here. Now we have our final nose cone segment. Then the nose cone just has a shoulder, so it just slots into place on top of there. So now have a high power rocket. All I got to do is add the laundry, add your parachute shock cord inside there. Launch lugs are built in, shock cord retention's built in, motor retention will be built in. If I decide today, hey, I want to fly, a 38 millimeter motor, well, I can unthread this part here and then thread in the new 38 millimeter motor mount. Now the rocket is a 38 millimeter rocket. Or the one I'm printing right now, I can thread in a triple motor mount, so 3 29 millimeter motors. I hope to launch this in May. NSL is in May. It's only 3 hours away, so I want to fly this in May. But hey, there you go. And I'll probably, actually, that's probably long enough. Where's my CG on this? Yeah, that's a pretty decent CG. That's not a horrible CG. Now that's going to shift back a little bit when I add a motor, and it's going to shift forward a little bit when I add laundry. I might add one more body tube segment. Make sure my CP is in a good spot. Yeah, that's the whole point, baby. Massive rocket. All 3D printed. There's going to be one paper part on the entire rocket. That's going to be the motor tube that's going to stick in here. And that will be the only paper part on the whole rocket and the only part that requires glue. No other part of this rocket requires glue. Because I don't have to glue on launch lugs. They're built in. I don't have to glue in a motor mount. It threads in. I don't have to glue in body segments. They thread together. It's all just threads together. And even the shock cord does not require any glue. Because these two holes right here is where your shock cord goes. So you feed your Kevlar down one side, back up the other side, tie a slip knot. That's all inside the rocket. And that would have, you'd have to pull this whole thing through the rocket, separate that shock cord. So no glue required. And if I want to add like an E-bay or a payload bay, I can easily do that. Unthread this section. And I can thread in a new section. So for example, maybe this will have a camera pod on the outside. And then re-thread in the nose cone section. Then pop the nose cone back on. And now you have a longer rocket. A separate avionics bay in the middle there, or a cargo bay, or a payload bay, or a camera bay. And it's all modular. Is it heavy? Yeah, it's heavier than paper, but it's also modular. I can take this apart, put it in a suitcase, put it back together again. If it crashes and I damage that part, I can take all the good parts off, take off the bad part, take off the bad part that got destroyed, print this new part in 5 hours, and there you go. Thread in the new part, and I'm all good to go. How cool is that? Now, my rocket's all restored. Or, if I'm bored with this nice, fighter jet style end, I take my motor mount out, I unthread. Come on. Oh. Unthread the 3-fin fighter jet fin can. Oop, what did I do? I unthread that, and I go to a more traditional missile 4-fin setup, and I thread that in there. And then I put my motor mount back in. There you go. I can make a new rocket. How cool is that? I mean, that's just badass. I love this. This is so much fun. The potential for what you can do with this once you have all the parts made, just really cool. And then the whole thing breaks down into no part is bigger than 400 millimeters. So the whole thing breaks down, and now I can stuff this in the car, put it in a box. Now this is just PLA, and this is just using this what is this one? WeDo ME40. This is the WeDo ME40. But any of these parts, you need a CR10. You need something that can print 334. But as you noticed, I'm also designing parts for shorter printers. So these are 245 millimeter parts. So like an Ender 3, Prusa, Bamboo, Odin 5, Neptune, a longer 3D. All those will be able to print the smaller parts. Your rocket will be a little heavier, but it'll still be just as cool and modular. The real advantage is this part here. Gives you 400 millimeters of length. Now, I want to print one of these. What I would really like to do, if I can get them to sponsor me, hey, ColorFab, you out there? Polymaker, you out there? I'd like to get some lightweight ASA. No, not really. The UV resistance is overblown. I've taken standard PLA parts and bolted them to the side of my business, and it worked fine for 5 years. The color went away, but who cares? The part was structurally sound. Now, because it's PLA, you do have a problem with radiation. If you're in a place where you have a lot of solar radiation, meaning a black car gets hot, then this is borderline too dark. Because this dark color is going to absorb solar radiation, which means it could be 70 degrees out, but this could absorb enough sunlight to heat up and start getting soft. So you do have to be aware of that. So you're going to want to print in light grays. You're going to want to print in whites, naturals, creams, khakis, light colors. So lighter than this. I just happen to have 2 rolls of this coffee color, so I used it. Although these 2 rolls were a different color. You can actually see the color change. You can see the color change right there. Changes color between the 2 rolls. Yeah, I might. I know one of them has a lightweight ASA. So they have what's called LWPLA, lightweight PLA. It's basically got a foaming agent in it. What you do is you print it too hot. Print it at 230 or 240 Celsius, real slow. And what happens is it foams up. So you could reduce your flow rate and allow the foaming action to bring you back to correct size. So you end up with a part that it's weaker, of course, because it's air-filled plastic now, but it'll allow me to make this part lighter and make it out of ASA so that it won't get soft in the sunlight. And while the part will be weaker, I think it'll still be strong enough structurally, because I use structural engineering to make it. All those lines, those are all ribs that connect the inside and the outside together. That's what gives this structural integrity. So, printing one of these with LWASA would be pretty bitchin'. I would need like 8 kilograms of the stuff, because it's probably going to take 1 kilogram of messing with it just to learn how to use it. And then each of these rockets takes about 2 kilograms. And so I'd want to print at least 2 or 3 of them. A couple parts and stuff like that. But yeah, being able to print this out of ASA would be pretty cool. And another idea I came up with was oh, you gotta mess with me, don't you? You put one of these launch lugs on the nose cone. I can't put it on the body. It's gonna take some trial and error, because what happened, I can't put a launch lug on here because I need to make sure the launch lugs line up. So wherever the launch lug is on here, it has to line up with here. But because they're threaded, it's hard to tell where it's going to line up without a lot of trial and error. Bit lines do not line up. So this one, here's the zit line on here, on this part right there. But the zit line on this part's over here. But in the program, they're in the same spot. So what I need to do is I need to That would be Ivan Miranda, and yeah, he's awesome. That's why. He's freaking awesome. I could make a short rocket too. I realized I don't have to use that body piece. I could just take one of these directly to a nose piece, and now you have a little stubby rocket. Now that one would probably require a little bit of weight in the nose to be stable, but could go the stubby route. Come on. Oh. Could go short. Then of course don't forget your motor mount of choice. Oh. I think I'm going to put indents in this. Give it a texture so you have something to grip. Right now you got nothing to grip. If this locks in place, it's really hard to turn this. Oh, hell yeah. Video, slow-mo, pictures, and high speed. And on board. Oh yeah. So my next, now that this is working out good, my next project is to literally make an avionics bay. So one of these, smaller hole going up the middle, so I can have a pod built into the side here for the camera. Because you bet your ass there's going to be a camera on board this thing. Launch a rocket without a camera? Nah. And I'll also get to fly my makeshift rocket. So there's still the crate that goes on the top here. Where'd that crate go? Bright yellow. There it is. There we go. That goes on there. And then I have the astronaut who sits on top here. He'll be the pilot, but that'll be the makeshift rocket. I'm looking forward to flying that. Then I'm also looking forward to flying the F-15. That's that cool rocket. This is for lower power stuff. This is real light. This is like 100 grams. So this will fly on, you know. That's going to be a fly. This is Blood of My Enemies Red from Alien 3D, which you can't get anymore, sadly. It's also all vase mode printed. Everything is built in. All I need is the paper tube up the middle for the motor. Even the launch slugs are built in. Just 3 vase mode printed parts. If you have a CR10 size printer, you can print these together as one part. So it would only be 2 parts. But to allow people with smaller printers, I made it 3 parts because that's as big as you can print on a screen. So 3 parts allows you to make a longer rocket. I mean, you could leave it short, and that does look pretty cool, but you're going to have to add nose weight for that to be stable. How high can you go? How much money do you have? Because that's the answer to how high can a rocket go, is how much money you got. Because money determines how big of a motor. So, assuming we go full segment, so means go this size. We go this size, and maybe one more section. This should be about 4.5 pounds ready to fly, maybe 5 pounds ready to fly. 29 millimeter motor, costing $40. You're probably looking at 500 to 800 feet. Not going to go that high because it's a big fat rocket and it's heavy. Now swap out the 29 millimeter mount for a 38 millimeter mount and put a K550 in there. 4,000 to 6,000 feet. My big 6-inch rocket went to 5,000 feet in Colorado. So this should go higher. This is lighter and skinnier. So maybe 6,000 or 7,000 feet. I wouldn't want to go that much higher, not without electronics on board. Because you go much higher, you're going to drift further away, and then you got to go chase it. I don't want to go chase it. But yeah, in theory, I could I could print out a 54 millimeter motor mount for that thing, add another body segment to shift the CP again, and you know, I could probably hit 10, 12,000 feet with that rocket before I'll start running into structural integrity issues. Meaning, can the rocket itself handle much more power? But yeah, 10,000, 15,000 feet should be doable, theoretically. But now you're looking at $300 for a motor. The cost goes up real quick. But yeah, here's a failed one. Failed here. I screwed up when I melded them together and didn't realize it. That's the segment. And I have another model I'm working on now. You guys are going to get a kick out of this. Well, you're only going to get a kick out of this if you know what you're looking at. And most of you probably don't know what you're looking at, but still it's pretty. This one. Nope, it's not that one. I'll switch screens in a moment. There it is. I fabbed up all the parts last night. I just have to print them. What's cool is that this one won't require any paint because I can actually print this in the appropriate color for the parts. So, Estes had a rocket called the Ramjet. What's the practical benefit of climbing Mount Everest? What's the difference between climbing Mount Everest versus climbing, you know, South Mountain here in New Mexico? Because it's there. You know, those boys who fly high altitude, you know, they get off on altitude. For them, the higher, the more fun. Just like a race car, the faster you go, the more fun. One of our amateur Rocketeers just made a flight past. Listen to this. This is not a misspeaking. Okay, I'm telling you exactly what it is. He made a flight to 239,000 feet. He went to space. Like real space. Like astronaut level space. No people, just a rocket, of course. But yeah, he flew an amateur rocket to 239,000 feet. No, well, what's the cost justification for the $5,000 in your motor in your race car? It's your hobby. It's what you do. Some people spend $1,200 on carbon fiber rims for their bicycle. Some people spend $1,200 for a larger motor to make the rocket go to 20,000 feet. That's all. Some guys spend $3,000 putting fancy rims on their car with things in the middle that spin. You know, it's just this. You know, I'm not an altitude geek. I don't need a high altitude. In fact, I don't like high altitude because, you know, it's whoosh pop. Gets boring pretty quick for me. I prefer going exotic. I prefer making interesting looking rockets or modular rockets like this. Things that I can do at home. But I'm also financially limited. I guess if I had a few $1,000s to spend on my rocketry hobby, that I'd probably make a couple flights to 15,000 feet just because I can. Just so I can say I did. You know, my highest flight is about 9,000 feet. That was, I don't really count that because it was basically a disposable rocket. It was a little tiny rocket. No, actually, it was a little tiny rocket about that big, where it was almost all motor. And it's what we call a teleporter or a neck snapper. You know, we call it whiplash. 3, 2, 1. It just vaporizes and teleports somewhere up there. That gets pretty boring pretty quickly to me. I prefer rockets that are more visually stimulating. But that's just because I'm poor and that's what I enjoy. I get far more fun out of making a wacky, weird rocket like this. But just because it's fun. But what's the point? What's the point of sticking a rocket motor in this and launching it? What purpose does it serve? None. It's fun. I like making rockets. Some people like making them go fast. Can they hit Mach 3? Can they hit Mach 4? And yes, there are guys who fly rockets at, you know, Mach 5, and they literally burn the paint off the rocket. The rocket comes down with the paint burned off. Because the friction, going Mach 5 or Mach 3 through the air. And well, anyway, this is the Estes Ramjet. It's one of my favorite rockets as a kid. So all it is a rocket with a smaller nose cone and these veins in the middle and the top and the bottom. So it kind of looks like a ramjet rocket engine kind of deal. Fins on the bottom and whatnot. And I realized, I was like, you know something? My modular rocket design, really ideal for making a big one of these. So I did. Over 1 meter tall, 4-inch diameter, basically a 4x upscale. There's already a guy who did. If you want to see that, Ben, it's actually pretty amazing. Not only did he engineer, design, and fabricate his own flight computers, software, and throttle and adjustable motor mounts. So, for example, the reason these rockets all have fins is because these rockets have to be aerodynamically, ballistically stable. So what makes the rocket go straight versus this? Well, the fins do. Well, you'll notice on real rockets like Falcon 9, Falcon Heavy, there are no fins. The rocket is literally a tube. Why? Because fins are only useful for the first 90 seconds of flight. Once you get up to where the air is nice and thin and you're starting to go into space, fins don't do anything. So they're excess drag and they're excess weight. So how do these rockets fly? Well, the motor is movable. So the motor on the bottom of the rocket sits on a gimbal. And when the rocket, and it will, when the rocket starts to do this, that gimbaled motor goes, and it does that and pushes the rocket back. And so the motors on the bottom of that rocket gimbal. They can actually change where the motor points. So when the rocket, which is unstable, they're unstable, when that rocket starts to veer off, that motor gimbal adjusts and corrects and puts the rocket back on the straight and true. Well, he built a model Falcon Heavy with a TVC, thrust vector control mount. So he takes a standard Estes black powder rocket motor, sticks it in this mount, and he has his own designed flight computer on board that can tell when the rocket starts to tilt and will actually adjust that motor to keep that rocket pointed. And he can even program flight parameters in. He can say, okay, when you get to this altitude, I want you to do a gravity turn and go that way. And it does it. If you go lose control, pop the parachutes. It does it. And not only that, he put a second motor in it, deployed the Falcon landing legs, and he landed the rocket under propulsive thrust. So he actually landed his model rocket just like SpaceX did. It took him like 3 years to finally get it to work, but he did it. So his Falcon Heavy takes off. The two side boosters separate and pop their parachutes. The second stage separates, fires its second motor, and takes off. The grid fins deploy, the landing legs deploy. The rocket comes down under grid fin control, fires a second motor, and lands under power. It's mind-blowing. If you want to check him out, go to BPS space. So BPS, the letters BPS space. Look up BPS space on YouTube. It's amazing. Oh, sorry, I'm yawning. It is absolutely bonkers amazing. It's mind-blowing amazing to watch him do that. The struggles he went through to get that damn thing to land. Oh, it cost him thousands. Thousands. I mean, he spent hundreds and hundreds of dollars just in motors, trying it again and again and again. Remember, each time he flies the Falcon Heavy, it's 5 motors. 3 motors in the booster, 1 motor in the second stage, and another motor in the landing stage. Which is why he switched over to his Scout model, which was a single motor. to take off and a single motor to land. Now he only needs 2 motors per flight. Because it was a matter of software. He had to, get the software adjusted for when to fire the second motor, how to gimbal it so that it's not moving sideways when it lands. Because what would happen is he would land with too much propellant and then it would take off again, or he would land with too much skew and so it would hit the ground and tip over. And it was amazing watching the progress of this happen. And it's not like he could make a second flight the next day. He would spend the next month or 2 making software corrections, rebuilding the model. I mean, just the amount of work he put into it, it was very, very good to see him finally succeed. It was amazing. Because that's something we've been dreaming about forever. The first time I saw someone do that is when I thought that, something that would be really freaking cool. Like 20 years ago, someone stuck a D motor in the nose of a rocket. So D motor to take off, and the nose cone didn't come off. It was a plugged motor. So it would go over, come back down, and it would start coming back down like this, and then he would light the motor in the nose. Now, he didn't do that to land it. He just did that for show, for effect. But when I saw that rocket come to a stop in midair, and then actually move up a little bit, backwards before it popped the parachute out, I looked at him and said, now imagine if you did that 10 feet off the ground and you timed it just right so that thing landed using the rocket motor instead of the parachute. Well, this guy, Joe Barnard, he freaking did it. And he designed an entire movable rocket motor gimbal system to do it, and he actually engineered, designed, and wrote the software for his own custom flight computer to make it possible. And he did it. It was the coolest thing. It was definitely go watch his video. You search for BPS Space, and you'll see his Falcon Heavy flight. Oh God, keep yawning. Absolutely phenomenal what we can do with today's technology. And a lot of it comes down to the microelectronics that we have, the little 9-gram servos, the the modern manufacturing process for the engines, so that they're consistent. Because you have an inconsistency problem with the engines. One engine might be a little heavier, a little lighter, a little longer delay, a little more thrust, a little less thrust. There's variabilities in the manufacturing process. But yeah, to watch him do that, that was just so cool. So I took this basic design, this ramjet, and said, let's build a gigantic plastic printed version. So these parts are surprisingly light. This one's about 250 grams. This one's about 210 grams. These are all stupidly light, like 30 to 50 grams each. The fins are 68 grams each. These are all vase mode printed. I've already got them all sliced up. I have the silver PLA. I got to go out to the bus and I got to find some orange PLA. Ice storms suck. Everything breaks. Everything gets heavy. So the way this would work is that these body tubes here actually have different slots. See how that's got a wider slot there? That slot is designed to accept these pieces here. So, this piece here would go in the bottom. This piece here goes in the middle here, and that allows that piece to then sit on top. This piece here is on the top. Nose cone sticks out the top. Now, I don't actually need these things here, but I wanted to make the fin attachment a little more firm, because on this rocket, you see how the fins stick out the bottom? That means unless I build a rig for the parachute, unless I have like a tether going to the back of the rocket, these fins are going to hit the ground. And if I just glued these fins directly onto the side of the rocket, it would probably break the plastic. So what I did was I engineered these little sockets. that are a little more built up and beefed up to spread the load from the for the fin, make it easier to attach. So you'd print 3 of these fins separate, and even the base of the fin, see, the base of the fin has the same curve as the body tube. So that fin will be a pretty good fit right inside that slot there. And then you glue it in place. But yeah, that's how I'm going to attach that. I'm also probably going to rig it. So I'm probably going to have a shock cord. Hey, TRT. And hey, Mike. I'm probably going to have a shock cord come down the side of the model. So there'll be a shock cord here, but then there'll be a second shock cord coming all the way down here to the back. And this way the rocket will recover horizontally. We'll have 2 parachutes dangling, holding the rocket horizontal. That will greatly reduce the impact force when the rocket hits the ground. So the fins should be able to handle that. They'll be vase mode, so they'll be pretty strong. But yeah, I did this yesterday. I got the idea and I was like, I have to do it. I have to build a 4-inch ramjet. It's such an ideal model for this type of treatment. Oh, it's just awesome. Now, this is going to be glued together. This is not going to be modular. I want this to be a whole lot lighter. All these plastic parts you see here, including 3 fins, 877 grams. So under 900 grams, to be over 1 meter tall. That's actually not bad for weight. That might even be lighter than a cardboard version, depending on how thick a tube you use. But yeah, now the only part that I'm not sure of, all these parts should fit together. I've gotten pretty good at modeling the tolerances. The only unknown is the nose cone. So the nose cone isn't hollowed out yet. It's just going to be a single wall vase nose cone until I make sure it fits properly. Oh, also, there's a bug in Tinkercad that's been causing me nothing but acid reflux and indigestion and heartaches and headaches and migraines. And I just want to find the Tinkercad team and beat them to within an inch of their life. I finally figured out the problem. You're going to get a kick out of this. So the problem I have is that I need this nose cone to be one piece. I then need to hollow out the middle of the nose cone. And then I also need to put these little slots in there so that I can print this nose cone. So you can see it's double wall. There's an inside and an outside. The shock cord mounts are built in. Everything's built in. You don't have to do anything to this nose cone. You tie your shock cords to these mounts. You put the nose cone in. This is very, very strong. You'd have to really squeeze the living hell out of this to break it. But what happens is errors would creep into the model construction, and those errors get worse and worse and worse until they actually begin to destroy your model. You'll merge the parts together, and the model will break. Defects will get added, just like random chunks of the 3D model will get removed or distorted. And it's basically, there's an error going on somewhere in the algorithm when Tinkercad works. And I finally figured out what that damned error is. This here, the bottom of this cone is very simple. It's a transition, cylinder, and a transition. Those are simple, basic shapes. You have a cylinder, and you have a cone, and the cone, you can actually pick a top radius, so non-zero, and a height. And as you can see, that gives you a transition. So that's how you can transition from one shape to another. So basically, this shoulder of this nose cone is 3 pieces. 2 of these, 1 of these. Okay? So that's no problem. When I merge these 2 together, so if I put this top layer here, and I make this 0, and then I merge them. Now you can see when they're separate, Oh, come on. There we go. Get this. All right. So that's where they're touching. And these are your two separate parts. Right. So this is not a problem. Let's increase the number of sides. So we have a smoother circle. Now, notice this. 64 sides. And notice this. 64 sides. That's going to become important later. So if I take this piece and this piece and put them together, why won't you let me do that without merging the whole goddamn shit show together? There we go. Now I join those two together. That's no problem. You can't even tell where they join, see? Now it's all one. Come on. Why does it do that? Look how much I'm moving and how slowly it's moving. But if I change the angle, now it's moving fast. That's another glitch they got to fix. But anyway, you see these parts are perfectly mated together. Well, here's the problem. If they're not perfectly mated together, I'm exaggerating this, but if I end up with these parts just slightly apart, now you see how it's dark in the middle there? That's because those two parts aren't actually merged together. If you zoom in real close, you can see there's actually a little tiny gap between those parts right there. See it? There it is. Little gap. Got a little itty bitty gap between those parts. Now, normally that's not a problem until I make a different shape. So let's say, go back, 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 back. Oh, it's doing it again. Get out of my face. So join these together again. Keep looking at the wrong screen and there's lag. Oh, you son of a bitch. It did it again. It has a fetish with grabbing all the damn parts on the screen. It's so annoying sometimes. It just makes you want to punch something. There. It's selected just those parts. So that's a perfect merge. No, it's not. What's wrong? Gotta get that to 0. There we go. Yeah, there's no line there. You don't see that disc inside there. That's what you need. You need this to be one uniform shape. Because otherwise, when you start doing things like this, create cut patterns, you start breaking things. And things start to get really weird really fast. All right, so separate these parts again. So let's make this top radius of 8, which means it's 16. Now I want to put a cone on top of here. Now there's 2 ways to make a cone in Tinkercad. Here we have 2 of them. One is I can use this paraboloid. So increase the number of steps. I think it's already maxed out. Yeah, 24. And so I need to make this 16 by 16. Jesus. How does that even happen? How did that even happen? It's off the edge of the screen. How? How did you do that? Look at that. Oh, Tinkercad, you can be so weird. 16 by 16. Actually, this is backwards, but you get my point. Oh, come on. Why do you do this to me? Why does it insist on grabbing this effing part? And let's join those together. Now, the other way to make a cone is to use a sphere, which is the way I prefer because you get a nicer cone. So you take a sphere, increase the number of steps. We have to do the same thing. We have to make it 16 by 16. Okay. And then what we do is we stretch this out, because this is going to be twice as long as what we need. So we need to make it about that big. Call it 66. So now I need to drop this by 33. Minus 33. Then I take a box like this, and I drop it through this way, and I cut the sphere in half. So now I have the half sphere, and again, I line the parts up. Merge them. Now, get rid of this line here. Now, if I take this one and look at it in hollow, you can see it is solid, all right? So there's no disc here, but it's not perfect. And you can see that here. Yeah, these little glitches. Yeah, they're not quite lined up right. That's going to cause defects later that the software is not designed to handle, and Tinkercad breaks itself when it tries to do something with that. This one's even worse. This one has a straight up disc. Now, remember what we said a disc means? A disc means there's a gap. But I put that on the 0 line. How is there a gap? Well, there is. It's a tiny gap, an itty bitty gap, but there is technically, if it'll ever let me move fine enough, actually get to where I need to freaking go, because Tinkercad sometimes sucks. Boy, can it suck sometimes. You can see, there it is. See? Those parts do not touch. And they have to touch. Because if they don't touch, there's technically material between them. There's technically an air gap between them. And when you start doing complicated things like shapes inside shapes and flattening it to almost a two-dimensional zero dimension plane, you start breaking the software. It gets very pissed off. And I spent hours and hours trying to figure out how the hell to fix this. And I finally figured out how to fix it. The only way to fix it, keep in mind, this is an improper cone. That this should be inverted, but it should be like this. You know something? We're just going to make you guys go away because you're really pissing me off now. Here's how I fixed it. How many pieces are there? There it is. That's how I fixed it. The only way I could fix it was I had to force this part and this part to overlap by at least 0.1 millimeters. And I also had to make both of them just a tiny bit bigger than I needed them to be. So this needs to be 125 millimeters. So both of these parts are 125.2 millimeters in diameter. That's why you see this jaggy pattern. That jaggy pattern is where this cylinder partially overlaps this blue cone and this purple cone. So as you saw in the previous model, the two surfaces did not mate together. And part of the reason for that is that the cylinders and cones can have 64 sides, while hemispheres or spheres, which is what this cone is, this is a stretched out sphere, can only have 24 segments, which means they can never line up. Every now and then, if you get a certain size, they'll be close enough and the software can deal with it. But unless you get lucky and you hit that certain size, you're either going to have surfaces that will not mate, or you're going to have an ugly surface where the surfaces don't quite mate up properly. When you're printing with regular printing methods, that's fine. When you're printing with vase mode, that's not fine, because the result is one strand doesn't sit on top of another strand. And so you end up with a weak point and the model breaks there. So what I had to do was oversize both the parts slightly, overlap both parts slightly, so that when I merge them together, this sleeve, this right here, this cylinder right here, this sleeve right here, see? That overlaps both parts slightly, and it cuts away the parts that are out of bounds. And it basically gives these two parts a perfect mating diameter. It makes them both the same 64 sides. So that's why you see these uneven lines here, because it's basically chopping away the excess part of this sphere that goes out past the 125 millimeter inside diameter of this cylinder. And when you join those together, it fixes the problem. And you can actually see that. You can see how you got like a triangle there and then an oblong here. It's actually, it's giving these two surfaces a common number of, it's basically putting 64 faces on the sphere. It's putting 64 faces on the edge of the sphere so that it can correctly line up with this transition here. And now when I make it hollow, it ends up perfect. And you end up with no discrepancy between the models. I must have spent 4 hours putzing around with these models trying to figure out what the hell was doing that. It drove me insane. I wanted to tear my eyeballs out. I was going mad trying to figure out what in God's name was doing that. It was making me so unbelievably angry. Oh my God, I wanted to murder somebody. I wanted to kill something. But now I know, it's easy to fix. All I have to do is make the two parts overlap just slightly. So, definitely don't want to lose my cone. I'll have to remerge these parts together again later. But now I know how to do it every time. So to make a really quick one, let's say I do a 20, increase the number of sides, and let's do this. So that's already a 20. Let's make the height 4, and let's make the top radius 11. Okay, and then move the top here again. Take my sphere, and wait a minute, I almost forgot. It needs to be 11. No, this one could be 11. Yeah, this one could be the exact size. This one needs to be oversized slightly. So 11.2, 11.2. Okay. Oh, it's double. That's radius. 22. The problem is I don't want 24 segments on my cylinders. I want my cylinders to be more round. But yes, in theory, that should work. Matter of fact, we're going to try that. That is a fantastic idea, Woozius. We're going to test that right now. Let's make this, let's do 80. And then we have to shove it down by 40. Oh, for Christ's sake, come on. Oh, negative 40. And we slice it in half. Of course I didn't go far enough. Of course I didn't. What else is new? I always do that. Always. Okay, there's the parts all lined up. Now, if I try to merge these parts together, this doesn't need to be that big. Go. So if I try to merge these parts together, of course it's merging with the rest of the parts on the entire build plate. I mean, God forbid if it would recognize that I wasn't touching anything else on the godforsaken, no good, scum-sucking, slimy build plate. Nah, it couldn't figure that out, could it? Just no possible way the software could be smart enough to figure out, I don't want that! Actually, you know something? Let's just hide it. Go away. Oh my God. It's like, come on, work with me here. There it goes. Now, if I merge these, you see I have a broken plane. These are not correctly merged. Even though this is on the zero plane, it's not merging. Now, the question is the gap actually created because there's a gap? Or is the gap because of the merge? So I'm going to try not overlapping these and do the cylinder sleeve and see if that fixes it. So the way we do that is we bring in a torus. We increase the number of sides to 64. Did I tell you to break apart? Do as you're told. So this is 11. That's 22. So we're going to pick a radius of 12 with a wall thickness of 1, which gets us to the necessary radius of this cone. So we align them, and then I should just be able to lift this into place till it overlaps. See? There you have that overlap. Now, because this cone is smaller, the overlap area is larger, but that's fine. Now, let's see if doing that alone is enough to fix it. Nope. I still have to overlap them. So even though it's on a zero plane, it's not actually on a zero plane. They actually do have to be merged. So I found the easiest way. That's why I had to make this a little bit bigger, so that they can overlap. Because if I don't make this bigger, they can't overlap. So we're going to go to 4.1. That forces an overlap, but now I need to make this 11.1. Base, top, yes. Now when I merge them, there we go. Now we get a nice cone, and perfect. See? No glitch, no line, no disc, nothing. Now we have a perfect cone. Now I can scale this. Now I can flatten this, make my cutout pieces, and it's not going to lose its shit because it technically has a glitch in it. Now let's try your method, because that probably will work. I'm not sure, but well, let's see this. It has more than 64. It has more than 24, but I don't know. Is it 24 around? So let's hide this, because you still have the overlap problem. Even if I make them the right number of faces, I still need to overlap them by just a hair. Let's get rid of this. Let's make it back to 11. Okay, and let's change the height to 4.05. Decrease the amount of overlap. Now let's change the number of sides here to 24. Okay, it's definitely more than 24. Can't see them. There we go. Okay, so it's more than 24. Is it 48? Yeah, I think it's 48. Yep. Okay, so the sphere actually has 48. 24 segments, 48 facets. So if I make these all 48, let's see if that works. Yes, that works as well. So if I change the number, I think I still have a small imperfection there, but I believe, oh, that's a dimensional imperfection. Hang on. Fix that. So this needs to be 22. Because we had an overlap. We created an intentional overlap. So this should fix that. Okay. Still not perfect because of that little tiny overlap there. What happens if I make this 4.01? There's only a 1/100th of a degree overlap. About. Still needs a little more overlap. This is not perfect. For some reason, I don't know why, it's not possible to bring the part to 0. I don't know why. It won't do it. It won't let me bring the part to 0. See how you got the little bit of tearing there? So it's not 100% perfect. I do not know why it does that. When you build native parts, you can 0 them. But for some reason, you can't 0 cut parts in all situations. You see, this is not a native part. So this part is actually not a cone. It's actually a sphere that's been cut in half. And for some reason, when I cut that sphere in half, it's no longer possible to bring it to 0. And I'm not entirely sure why. I wonder if the way I make the model is the problem. So what if I do this and I put a plane here? Now I get rid of this and I put a new box. What I've done now is I've formed the I've formed from the bottom instead of from the top. Will that be 0 now? Find out. Nope. Still has a glitch. This line shouldn't exist. Yeah, there's no line between this and this. That means the two surfaces are perfectly mated. It's close, but it's not perfect. And that will cause glitches the deeper you go into the model. I've had models where I have glitches that are so bad that the only way for me to fix it is to export and re-import the model to destroy all the history. And then the model becomes more simplified, and I'm able to, like those little things that I put on the side of that orange tube to stick the fins in, those became too complex. I had to export that as its own part, re-import it, and then it became a simplified part, and I was able to use. Obviously, I could not then edit it any further because I exported it and re-imported it as an STL. But yeah, it's basically. I guess it's to the point where I'm doing things Tinkercad wasn't really made to do. It's like I'm abusing Tinkercad a little bit. But yeah, that I can't even accept that. That's a problem. That has to go away. So the easiest way to make that go away is to make these parts just a hair bigger. So this needs to be 22.1 by 22.1. I need it to be large enough that I can cut away material to make it, and I might as well go back to 64. No reason to stay at 48 if I don't have to. Now what would solve this is a half sphere. If they provided us with a hemisphere, they do. Oh, they do. Hold on, let's try that. Delete. Let's bring you back down to 48. Let's bring you back down to 48. You are at 11 like you're supposed to be. Oh, maybe that's how I got around that problem in the past. Put the work plane there, drop a hemisphere on here. 22 by, not 222. Dumbass. 22 by 22 by 40. Let's see if that works. How much you want to bet it does? Nope, still glitches. Oh, interesting. No, it's on there. I have new glitches down here that didn't exist before. Those didn't that intersection did not glitch before. But this one is cleaner. This is a cleaner joint, and for making a simple cone, this will work. For making the complex cones I make, this won't work. Why is that joint no longer perfect now, though? $48. Oh, this is still 64. That's part of the problem right there. Okay, let's try that again. Okay, so this is back to being perfect, but this is still imperfect. I don't have to do the merger, like the overlap like I did before. I no longer have to do that, but I still have these little tiny, very vague, slight imperfect. This line, this circle should not be here. It should be invisible like this one is down here. And if that circle is visible, that means there are slight variations in the surface there. And those slight variations will cause you a nightmare. Now, because they were on the 0 plane though, I might not have to do the overlap anymore. I might just have to oversize this just a hair. Let's try it. Get you back to 64. Get you back to 64. Let's oversize you. Let's try to do it just 0.1. 22.1 tab 22.1. Okay, let's bring in the sleeve. Line everything up. Yeah, that's looking good. The important part is that none of this pink makes it all the way down. That's the important part. As long as none of the pink makes it all the way down to the bottom, that means it's fully merging the two surfaces together. If any of these pink spikes make it all the way down, you got to oversize the part a little bit more. And almost perfect. Now, is that a gap, or that line shouldn't be there? Why is that line there? Oh, maybe I need to oversize the other part as well? Maybe by oversizing both of them, they are still aligned. Yep, there goes. So there was remnants of the original transition. So you have to oversize both by 0.1 millimeters, and then you get a perfect join. No lines. That's the important part, is making sure there are no lines. Okay, so by using the hemisphere, at least I don't have to overlap the parts this way. It'll actually sit on the zero plane like it's supposed to. I just have to make them both 0.1 millimeter oversized, and then use the sleeve, shave them down until they're perfect. You can see that here. You can see how it's almost doubled it. See how this is a facet, and how it's, yeah, you got that little nook here, and it's almost doubled it so that it now matches up with the facets on this one. Basically, both parts are going to assume the number of facets of this part, and this part is limited to 64. No worries, DeWitt. Check out the rocket. Finally finished all the parts. Gonna get a kick out of this. So there is the complete rocket, all 3D printed, and all these parts thread together and fit together. So this is the motor mount in the bottom here. There's the interchangeable motor mount. And these all these parts thread together. This part is a sleeve fit. The nose cone simply slips in there. And I can break down the entire rocket into its constituent components. All this breaks down individual parts. Then I can add segments, remove segments, repair segments. So if I want to make the rocket a little bit longer, add a section to it. Avionics bay I can add to it. Cargo bay, I can do whatever I want. It's all threads together, fits together. How cool is that? I can't wait to fly this. This is great watching this fly. Yeah, there are rocket motors where just the motor is bigger than this rocket. Just the motor is bigger than that whole rocket. Yeah, like an O50,000. It's like a $3,000 rocket motor. Oh yeah. If you got the cash. Yeah, they fly. They're one of our members just flew an amateur model rocket, a civilian amateur model rocket, to 239,000 feet. He flew to space. No, not him, just the rocket. You know, nobody was in it, of course. But he flew a model rocket to space. Yep, I saw that, and they're already working on 5.02 because there are some other fixes that need to be made. So it looks like they're going to keep updating. Let's hope they keep it up. I finally figured out a long-term bug in Tinkercad that's been driving me absolutely insane. And it turns out what I need to do is I have to put a sleeve around the outside of these two parts because these two parts do not perfectly mate together. And when these two parts do not perfectly mate together, you get this. And when you get this and you make it hollow, you can see it's not a perfect mating. It's pretty close. But you see that line? That line shouldn't be there. It should be like this, totally transparent. Well, it turns out if I oversize both parts just a hair and then use this sleeve, oh, Jesus. Sorry about that. So if I take these parts and join them together, do not get a perfect joint. See, they are not perfect. That's actually pretty close to perfect. I'm actually surprised how good that is. But these parts are not, you can see how they're not exactly aligned right? And that causes big problems down the road because that defect adds more and more defects, especially when you start doing extreme things like squishing it to a two-dimensional plane so you can use it as a cut tool. That really pisses it off. Unless the part is perfect. And the way I got around that was to put this part is 0.1 millimeters too big, see 11.1. And this part is 0.1 millimeters too big, 22.1. And then what I'm doing is I'm basically making both parts too big, and then I'm using this sleeve here to cut off the excess that's sticking out past 22 millimeters, because the inside diameter of this is 22 millimeters. And by cutting away the excess of both of these parts, they now have a perfectly matched combined mating surface. And when you join those, you get perfection. See no ring? Notice there's no ring? The only reason you even know that's the joint is because that's where the cut plane is. If I take that away, you don't even see it. See? Perfect. Now this model won't glitch. That is a problem that has been driving me crazy. Now, when I was doing regular cones, it wasn't that big of a deal. But when you start doing vase mode cones, the joint really needs to be perfect or it breaks vase mode in the slicer. And turns out, there you go. So, and the primary issue is that this is capable of going to 64 sides, while this is only capable of going to 48 sides. If the sphere was 64 sided, if it had 64 segments, it probably would be okay. And it would, because you notice I can merge these two together. Get that out of the way. I can merge these two parts together. No problem. Perfect merge. But as soon as I add in this part, whoops. As soon as I add in this part, no longer a perfect merge. See how you can see the circle? And sometimes it's even worse. So, once I make them a little bit too large and I allow them to overlap, then you get perfect merge. Zero errors. Basically, the cylinder creates a mating edge. It cuts away the excess material from both pieces so that they have a common mating edge. But now I can make proper nose cones without Tinkercad and my slicer losing their shit. So, yeah, that makes life a lot easier. Oh boy, does that make life a lot easier. Now I can stretch and distort this if I want to, and it's still a perfect merge. So that's nice. It took me 3 or 4 hours last night to figure that out. I finally got fed up with it. I was like, one way or another, I'm fixing this goddamn problem instead of coming up with hodgepodge solutions to make it work. I also figured out another neat trick. I figured out how to make my fins. This is really cool. It's a lot of work, but it's cool. Let me show you this. We're now getting into some very advanced Tinkercad stuff here. And I'll start from scratch. So. Oh, I might have gotten rid of it already. Yeah, I already deleted it. Okay. I'll just use this one. So I want to make a fin with this shape. So how do I make a fin with this shape with an airfoil like this in Tinkercad? Because Tinkercad does not have a tool to make this shape. That doesn't exist. The closest I can get is to take a cone like this. I use a cone because it allows the most number of sides. Okay? So we're going to give it a top radius. Go as much as this will let me go. So here we go. Now we're going to start creating a fin shape. Now, there is your basic airfoil fin shape. Make it an even number. So here's your basic airfoiled fin. Now, if all you want is a fin or a trapezoid style fin, this is actually good enough. Because I can actually change the base radius, make the base thicker. Yeah, I'm getting that nice little trapezoid fin shape. Okay? But what if I want a shape like this, where this line and this line are a different shape? Okay? I can get close to that by simply doing this. What I do is I'll overlap them a little bit. I'll bring in my template. And I'll use this fin as a template. Okay, so can I get close to this? Let's find out. I can't go any lower there. Gotta go out more here. Increasing my top radius a little bit will help. Okay. So that gets me pretty close. Now, I can pick one of these edges and make it nearly perfect. Okay? So let's say I want this leading edge. All I gotta do, come out here like this, and just start doing this until they're pretty close. Bring them more in line. We're not quite there. And I'm going to probably call that good enough. It needs to be about 0.5 degrees more. What I'll do is I'll do this. Come on. We're going to go -1 is too much, so -0.5. And that's pretty close. Okay, so we have our leading edge right about there. Okay. And I can stretch this out. Cover up. Oh, no. That one. I can stretch that out to cover up the tail end. And there, our leading edge is pretty spot on. All right. That's pretty close. That's close enough for government work, right? But here's the problem. That doesn't give you an airfoil fin. So I can put a work plane on the top of this shape. Okay. I can now cut purple fin this way. That looks good. I can also put a work plane on this end. And I can put a box here. Then this out. And there we go. So now I can cut away all the excess crap. So I take this box, this fin, and this box, join them together. So now I have, oops, I gotta extend that box out. Come on. You see how it always puts the UI right where I gotta click? They should program it not to put the goddamn number box on top of the grab box. How hard is that to figure out to do that? Move them apart. Oh, some design choices are just so dumb. Like, come on, Autodesk, use your brain. All right, so I got my leading edge, I got my trailing edge, and I got my my root edge. Now I need to create a box to get rid of the top edge. The back edge. The way I'm going to do that is I'm going to do this. Then drop you down and through. And what I'll do is I'll just bring this whole entire kit and caboodle. I'll bring you down. Here we got to rotate. And close enough. Bring you down. And I'm going to call that good enough. So now I need to select the purple and the clear. And there you go. Now for a lot of people, oh, wait, what the heck? Why is that? How did that happen? Oh, the orange is not above the plane. Duh. Because it's sticking out. That's my fault. I need to bring this out this way a little bit. Then I need to raise this up. And, oh, we're not even close. Okay. Rotate. There we go. Close enough. Now, I could just leave it at that. And there we go. I now have the same shape fin as that. But it's not an airfoil. As you can see here, I'm on the wrong screen again. They have the same profile, so they have the same outline. And this has a nice curved leading edge, but it does not have a nice curved trailing edge. Okay? So this fin is largely flat on the trailing edge. There are 2 ways I can fix this. Maybe 2 ways. I can create a model that's going to split this model to merge with this model. So I would want to make these the same thickness. So this one is 25. And we're going to make this one 25. Now they're the same thickness. And what I can do is I can find the point at which these models merge, which is going to, you can almost see it. See that line right there? That's kind of where the front half changes the back half. So the way I would do that is I would unjoin this, and you can see I have two different pieces here. So what I would have to do I would have to bring that other piece up. So I'd have to duplicate this. And let's move it to the side a little bit so we can see the two pieces. Okay. And I would have to bring this piece up to match the 0 line here. So if we bring that to 0, that's not 0. That is 0, actually. How did I do this yesterday? It was very annoying to do, but it was doable. I need to make this trailing edge match the bottom. Just like that. Now I bring it down so we get to 0. So now I have my leading edge and I have my trailing edge. I guess the easiest thing to do would be to make it more visible what I'm doing. So for example, we don't need, I'm trying to figure out the easiest way to describe this. I'm basically cutting the two parts in half and I'm going to merge them where they overlap. All right, take these two parts. That's our leading edge. And that's going to be our trailing edge. We're not quite getting all of it. I'm not smart. Okay. Now we have our two halves. Change the color of this to something else. Line them up. Okay, so now what I need to do, get rid of where they overlap. Now there's a couple different ways you can do that. I need to move this point. Probably just stretch it. I don't know if that's smart or not, but I'm going to do it anyway because I'm lazy. $25. I think I'm doing this wrong, but we're going to go with it. There we go. So now we have a common point. I can also get rid of the excess. This needs to be a little bit longer. That point needs to come out past there. So we put the plane on this piece here. I think there's a better way to do it than I'm doing it. Okay. That takes care of that. takes care of this. So now we have our shape, we have our leading edge, and we have our trailing edge. Now, do you see this line right here? That line is where the two parts overlap. So what I need to do is put a plane as close to that line as I can. And cut these parts, cut them away as close to there as I can. And probably the easiest way to do that is to use, oh, it's different on both sides. That's annoying. No, it's about the same. It's about the same. So I think the easiest way to do that, now I can get rid of this since I have the shape now. Bring it down, then rotate it. Try to get that to be almost level. Boy, that's pretty damn close. That might be close enough for government work. Come on. They always make it so difficult. You can't rotate when you're look how big the fucking rotation circle is. Why does it need to be that big? Why does it need to be bigger than the whole freaking screen? Because the only way to get a fine movement is you have to be out here, all the way out here, where it finally gives you the freaking little number box. These little UI things where they do this, where it's so annoying. This UI, this user interface for rotating these parts should scale with the zoom level. First of all, this should be in here, and it should be off to the side so it doesn't accidentally get clicked when you're trying to grab this. There's nothing worse than you're trying to grab this little freaking anchor here, and you keep grabbing that because it's on top of it. Their UI should be smart enough to go, oh yeah, we don't want those to be on top of each other. It's like, come on! This is 101 kind of stuff here. This isn't rocket science. But that might be close enough. Okay. Now, the blue is the bigger one. So if I remember correctly, I'm trying to remember how I did this before. I think I know what I need to do. The blue is the bigger, so you want to use the green as the anchor. Now, the closer you can get these to align to each other, the better. So you take a box. God, I keep using the wrong screen. Take a box, and we make that box as big as the whole thing. We make sure we cover up all of it. So we passed into the blue area, and we got it. So now what I do, I take the green one, I duplicate it, I turn it into a hole, I select the red box, I join them. That gives me a hole for that half there. But now I need to do another half. I think I'm actually a little bit wrong on this. Hang on. I think this needs to be exactly where there. Okay. And then I do a Control D on the red box first, and I bring the red box up above the blue box like this. And then I hide this one. I take my green box, that's a hole, join it with the red box, merge, turn that into a hole, and I then merge the clear box with the blue piece. That trims away all the excess blue on the bottom, see? Yeah, now they overlap. And now I bring my box back. Come around to this side where I can see the blue. You do want it to be totally covering. I think you do want it to be totally covering it. Otherwise, you can get glitches. So you keep swiveling it around till you see blue. Okay, I grab the blue one. Control D again. Turn it into a hole. Join it with the red box again. Join. Turn that into the hole. And we're going to join that with the green one. And there we go. We now have a fin that has an airfoil down the whole length. Not perfect. There are better ways to do it, but it's pretty damn close to what we want. I think I needed to cut away more of one or the other in order to have more curve. And now to get rid of these lines, join this together. Because you see, we have those lines. See, we don't want those lines. We want those lines to go away if possible. And this one has a lot of them because I didn't do a very good merge, but I think you get the basic idea of what needs to be done. But what you can do is figure out which surface is higher. There we go. That's getting rid of it. And you use that to get rid of that excess. Merge. Did that work? No, that didn't work. So there. Okay, so that was the wrong surface. It must be this one. There we go. Yeah, you got that little band. It should be cutting away material there, I hope. Still not working. I'm doing something wrong. But you get the basic idea. I got pretty close. But there shouldn't be 3 lines here. That's a pretty bad crop. I did a pretty bad job on that. But it's getting there. It's getting close. But you can see now that's how you get a more complex airfoiled fin shape. So now I have a fin that looks more like the original fin, and it's got a curve shape throughout. You take the commonness between the two curves and you join them together, and you end up with that. If the more precisely you get this alignment done, the more precisely you align these parts, the better your merge will be and the less artifacts you'll have. Because they will cause problems, especially with phase mode printing. Of course, I left a little chunk on there. That shouldn't even be there. I don't even know how that got there. How did that even happen? Oh well. See it's starting to glitch? See it's starting to glitch? It's starting to glitch already. Look. Watch. I joined these together. Watch this corner here. Watch that corner. Where the hell did that come from? It's glitching because I have these near 0-dimensional overlaps. So I have to adjust my model to get rid of those near 0-dimensional overlaps. We're talking like 0.1 millimeter here. Yeah, it's got a tiny little hole there. Yeah. Yeah. A tiny little gap right there. It's freaking out the software, and it doesn't know how to handle it. And it gives you crap like this. Oh, it drives me nuts. But there's ways to get more complex models inside. Sometimes even just rotating it will make it better. See if that makes it better. Yep, got rid of that mark. So you see, it didn't create that little... It didn't put that stupid little piece there now. Sometimes just rotating is enough to get rid of it. But that's the basic gist of how I made that fin. What a pain in the butt. Oh, God. Thankfully, mine only had a tiny defect, and I was able to get rid of it pretty quickly. This was a fun model to make. When I made this here, this one was a whole ton of fun because it's no longer symmetrical in a circle. It's no longer radially symmetrical. As you can see, these are all different lengths. Now, for regular printing, it's a non-issue. You print it with a single perimeter and, I don't know, 10%, 12% infill, and you're probably fine. But I'm a glutton for punishment. And I want my goddamn vase mode. I'm greedy. I want my vase mode. So, what I had to do, there's a couple different ways to do it. First, I had to figure out my pathing. So I have to connect all of these surfaces together into one single surface, but I can't connect them twice. You cannot connect twice to the same surface. You can only connect once to each surface. If you connect twice to a surface, you create an island, which you can't vase mode. So if you look carefully, you'll see this is the line connecting the outside to the inside. That line goes through here, but comes back, through here, but comes back, goes all the way down to here, opens up into this one. Now this surface is connected with this surface, and then one line goes into this one line goes into this one, and one line goes into this one, and it terminates. So it'll come in, around, up, over here, around, over here, around, over here, around, back into here, over to here, back into here, over into here, back into here, around, and then back out again. So that is one continuous vase. These are ribs. So this goes to within 1.2 millimeters of this. So it touches, but doesn't pierce. Same thing with these. It was easier to do from the inside. What I did was I created a radial array of these. You'll notice these are all the right angles. They're all the, see how this one lines up with this one lines up with this one lines up with this one. I created a radial array, split them in half, got rid of all the inside halves. I added ribs here to beef up the connection between these two. I added ribs from out here to here to beef up this intra connection between the three. And then all of these ribs, I cut them 1.2 millimeters short of these circles. I basically had a second set of circles. I made them 2.4 millimeters diameter larger, which is 1.2 millimeters each side, and used them to cut these cuts 1.2 millimeters short of reaching. So that from here to here is 1.2 millimeters because I'm using a 0.6 millimeter nozzle. And I did that. I did it right. I didn't screw it up. And the result is this whole thing vase mode prints. It's just really cool to watch work. to see it do that. Because vase mode's perfect. There's no retractions. There's no travel movements. Just continuous extrusion from start to finish. So once your first layers go down, as long as nothing separates those first layers, it pretty much can't fail. It's very rare for a vase mode model to fail. The only thing I want to correct is that this here is a little too steep when I join with the other model. So I want to rework these threads a little bit. I'd like to make the threads a little shallower if I can. See, right now they stick out this far. I'd like to cut that in half. Because if I can cut that in half, then I can make my the structure inside the rocket smaller. But I might be better off leaving it thicker and simply increasing the density a little bit, so that I can use a shorter threading unit. So how would I describe that? The best way to describe that would be to go to a tube. So we go to something like this. So what I need is that piece right there. Copy. We're going to go to a new workspace so we don't screw up any of the existing good models. Okay, this is my my Shop Time shirt. You guys watch Shop Time? Another good channel. He does cool things with epoxy, bathing, and stuff like that. I like his stuff. Okay, paste in the model. Okay, so what I would like to do is to how would I improve this? All right, how big is this? This is 125, correct? Yes. So if I want to go maximum thinness, but see, I like a 4mm wall, so I'm okay with it taking up 4mm of space. The way we're going to do that is we're going to put a chorus in the middle. We're going to align these. Now, it's very important when you're messing with shapes like this, you have to remember this does not have a symmetrical center. This does. All right? That's because this is oblong. Yeah, it's thinner over here, and it's thicker over here. So this is going to be a slightly asymmetrical shape. But because this transition is larger than any point on this model, the common center point is the center point of the transition. If you're going to be messing with asymmetrical parts, easiest way to deal with that is to drop down a disc substantially larger than your part. So let's go 222 by 222. Right? Keep using the wrong window. Make it tiny. Okay. While you still have a good, proper common center, use it to center the parts. Okay. And then just drop this disc down to Never Never Land. All the way down here. Now, let's say this shape was slightly oblong. If I rotate it, it's not going to rotate around a common center because it's an oblong shape. However, if I join it with this shape, because this shape is bigger than this shape in all dimensions, they now share a common center point. Gotta give it a second. I shouldn't have used that part to demonstrate it, but now when I rotate it, you'll notice. What is happening? Here it goes. See how the oblong itself is moving, but it's staying around that common center point in the middle there? That's because you rotate around the largest object's center point, which is this thing down here. So you do is you keep yourself a little piece down here. You can't make it transparent, but you can make it less obvious. Transparent will help a little bit. Just you have to make it back into a solid before you merge it, because if you merge it transparent, it goes away. But that would allow me, for example, let's say I want to, I want to have this sticking out the side like this. But now how do I rotate this around this part? How do you do that? You can't. If I take this and try to rotate it, it's not going to stay with this. And if I merge these two together, then this part is going to rotate around its common axis, which is going to be different. Watch. See how it's shifting? See how the purple part is shifting? I don't want that purple part to shift. So what I can do is I can join this. This already shares a common center with this. So I can use this as like a pull tag. I can grab this and this, join them together. Now watch what happens. See? Now I can rotate it around that common center point. Isn't that cool? Where does this come in handy? Well, this comes in handy if I want to put something, symmetrically around an object. So first, let's unjoin these. Now let's take these two parts but just line them up, keeping the purple part frozen still, but line them up on center. Okay. Now what I can do, I can take this part and this part and rotate them as a common set. I don't even have to join them. See? So now I can take this one and duplicate it, pick one of them, select that part, and now I can rotate. Let's say I want to do 3 of them. That's 120 degrees, which I'm going to, there it is, 120. All right. Now I unselect. I select just that. I duplicate it again. And then I select this and rotate it again. Go to 120 degrees again. There. Now I have these 3 pieces radially symmetrical with the centerpiece. And now the problem is this part here is no longer radially symmetrical. Well, it might be. Is it? No. See? 133.5 by 125.66. So if I rotate this part, it's going to start shifting. See? See how the purple part's moving? That means the purple part is not staying around a common center. So again, I can select everything, including my helper disk in the background. Now we are symmetrical. You click here, 227.8, 227.8. So we are planarly, radially symmetrical. Now if I grab this, you'll notice the purple part's not moving. See, the purple part's staying put because I've given it a common center point to allow me to rotate. This comes in so handy when you are making radially symmetrical objects like rockets, where you create asymmetry because of the way the parts work. It's very annoying. But that is a way for you to keep that symmetry. And then you just remember when you're done, you join everything together without the helper disk. Just don't include the helper disk when you merge the parts together. But just remember, if you move this part relative to this part, you've broken your symmetry. And it's a lot harder to get it back. It's a lot harder to get it back. There's ways to do it, but it's a pain in the ass. So you want to keep that little helper disk there at all times and always make sure that helper disk is bigger than you intend the entire model to be. And this way you don't lose your symmetry. That's a handy feature for Tinkercad. You just, you do that, but the thing is, you cannot move this part and you cannot move this part. At least on the plane, you can't move it and you can't rotate it. Well, these I can rotate because they are symmetrical. Oh man, I was gonna choke on that. It was so bad. Now, are you unsure if your part is radially symmetrical? Well, that's easy. Select the part and pick a corner. As long as these 2 numbers are the same, you can safely rotate the part. If these 2 numbers are not the same, you cannot safely remove the part without losing your symmetry. So what you have to do is, before you move this part, while you still have a common center, so for example, let's say I'm going to add a square fin to the side of this let's say this is a rocket, and I'm going to add a square fin. Okay? So I can center the fin on this easily enough. All right? All I got to do is pick this, hold down the shift, pick this, select my alignment tool. Before I do anything, press shift again and select the anchor. There. I've just told it, move this, don't move this. Now I can pick my center point. Okay. Now, this is centered on this, but I cannot rotate this anymore. So let's join this together. Now I have this part. I can't rotate this. If I rotate this, you can see it moves around a common center point. Right? And you can tell when you click here, look, 162.5 by 125. That means it's not symmetrical radially. All you have to do is make sure your helper disc is bigger than the biggest dimension. This biggest dimension is 162.5. This one is 227.8 by 227.8. It's symmetrical and it's bigger than this. So now I just select both, and now watch what happens when I rotate this. See? The purple part in the center is not moving. Because I'm rotating this around the orange disc's common center instead of the purple part's common center. And that allows me to do that. Okay, that's important. Let's see here. What else? Oh, yeah, we wanted to work on this. Okay. So, the question is, should I modify these threads or should I start from scratch? I don't know. Let's decomplex the model first. I'm going to keep this, but no, I'm not going to keep that. I can always make another one. I did that to get rid of this little bit right there. Okay, let's break it apart again. So I want to select everything, and then I want to deselect green and purple. Goodbye. There. Now we don't need to, we're going to mess with this too. Again, select everything, deselect green and purple. And then this is probably a complex shape still. Yes. Delete the, no, wrong part. There it is. Okay. We know we are as simple as possible because this can be still broken apart. I'm going to get rid of that for now. I can always add it again later. Okay. Can it be broken apart anymore? Yes. Good. Let's get rid of that too. Any more? Yes. Any more? Yes. Delete. Okay. Let's get rid of everything. Okay, we are down to our basic threaded shape. You can see I can't break it down anymore. Okay, I definitely do not need everything below that line. So I can delete all that. Okay, there's our basic threading. Now, I could compress this. That will bring our threads together like that, which will keep the 3 lines of threads, so I'll get that locking nature. But the problem is I'm flattening out this angle. This angle is getting really flattened out by doing that, which is going to be harder to print. But I can also thin the model out a little bit. Now, is this model symmetrical? No. This model is 115 by 112, which means I'm going to need a common center point. I'll be using this disc. So let's take a torus. Let's make the torus bigger. Let's increase the number of sides. We can increase the height. Turn it into a clear. Now what I'm going to do is I'm going to align. Now, I already know this piece is centered on this piece. So as long as I do not move these pieces relative to each other, I'm good. So I just got to make sure I do not move either of these pieces unless I move them as a unit. Because if I move them separately, I break the symmetry. So I'm going to select this piece and this piece. We're going to align. We're going to hit shift again, and we're going to pick one of the two pieces. We're going to pick the orange one. So now the orange piece is going to act as an anchor, which means instead of both pieces moving to a common center, this piece is going to move to this piece's center, which means we have not broken the symmetry of our disc model inside here. Now deselect them again. So now what we can do, let's see. I want at least 2 perimeters. Is 3 millimeters enough? If I have 3 millimeters of depth plus the outer wall, that's 6 millimeters on both sides, plus the 0.6 millimeters on both sides. That's 4.2 millimeters. I want 3 millimeters of teeth bite, and I still need the 1.2 millimeters for the wall thickness. So that means it needs to be 8.4 millimeter delta. So I need an 8.4 millimeter wall thickness. 8.4 wall thickness with a radius of 62.5. There we go. So now what I can do is I can grab this part. Here's a neat little trick. If you want to scale an entire part evenly, so all the dimensions evenly, what you do is you pick the center point, you hold down the shift key, and then you pick the center point and lift, and that scales the entire part without moving its center line. What I'm going to do is I'm going to keep shrinking until I can just see the inner wall. There. That's 61. Now if I hold shift and click here, I can now let go of shift and it'll maintain that separation. 61.5. And hold down shift again, select here. Let's go 61.75. There. We are just touching the inner wall. I think I did that wrong. I think the dimensions are too big. No, wall thickness has to be half. I'm sorry. So 4.2, because this is all radii. I forgot. This is all a radius. So now we're going to do the same thing. We're going to change our resolution to off. Grab the center point, hold down the shift key, lift until we just touch the inner wall, just like that. Okay. That gets us our size. Now we have to change the size of the thread. So that now we've scaled the root of the threads. Now we have to scale the teeth of the threads. So that's to the inner wall, which is what I want. Now we have to change this to, I believe, 1.2. 1.2. And I should now be able to cut off the teeth using this cylinder. And that should give us a new tooth profile. Like this one, and this one. And select that. That should allow a 125 millimeter wall, 2 perimeters thick, to still vase mode print. So these threads are now as close to the outer wall as it's possible to get while still having threads. And while still giving me 3 millimeters of pitch. Okay. Do I see any angles that look weird? I don't think so. All right, let's test it. Do I need any more of these threads? No. In fact, I can get rid of some. Let's get rid of more thread. I want to go all the way down to... I want to go down to straight wall because I want it to be... I want to be able to bring it down to 2 perimeters, so perfect vase mode. So I do need a little bit of rise. I do need a tiny bit to allow me to conically shape that. Okay, now I need to move this thread point back to here so it forms a cone. The way I'm going to do that is by putting a box in here like this. Like that. Lift this up until we are fully above those thread lines. I need to go up a little higher. Actually, I don't need to be all the way over here. Well, this can come this way. Like that. Okay. Then I bring this down until it's inside the thread line. Yeah, I got to be below the thread line. I got to be inside the threads like that. I am not quite there. This needs to come up just a hair. Okay. Now what I'm going to do... And I'll export and re-import this to get rid of the complexity. So I'm going to turn this back into a piece. We are going to duplicate this, turn it into a hole, join it with this, cut it. Now I have a little cut tool that I can do that with. To get rid of any excess, I'll have to get rid of that later. That allows me to bring my thread line back to there. I'm liking what I'm seeing. Okay, we might as well get rid of that in this operation while we're here. There we go. Okay. Going. There. Well, now we still have our 3-layer thread, which should give us good locking. Looks like it's 2. Never actually becomes 3, but we do have 2 with 3/4 of a rotation. I think that's going to be good enough. Now what I'm going to do is bring in, let's bring in a block like this. Let's rotate you 90 degrees. Bring you up here. Turn you into a cut. And bring you in here like this. That looks good. Okay. Okay, this is looking good. Now, how do I create a center point? This needs to have a cone attached to it so that it always has a center. I know how I can do it. Okay. Let's bring this to the 0 line. See, once I save this and I bring it back in, it'll no longer have a common center point, but it does. I can merge it with itself. Okay. So, tremendous jobbin'. Let's export you and make sure you can actually be sliced in vase mode without too much difficulty. Okay, get rid of you, remove you. We are going to go to 0 top, 0 bottom, 1 perimeter vase mode. And I would like to stick with 0.3 millimeter layer heights if possible. All right, tremendous jobbing. Slice me. Yeah, it's not going to work. Maybe. I don't like the fact that I can see through that. No, it's too extreme. I think that's see they don't overlap enough. The only way that's going to work is if I make it taller. Okay, how tall do I have to make it and have it still work? Unlock. Let's try 50 millimeters. Okay. That does look better. That's about a 45 degree. I mean, that's pushing it, but I think it'll work. I mean, I know it'll work at 0.2. Let's get rid of that. Let's go back to a regular shirt. 2, 1. Now, I know for a fact if I go down to 0.2, it'll work fantastically. Yeah, see, that's nice and solid. So, absolutely works at 0.2. Doesn't work quite so good at 0.3. Is it broken anywhere else? Looks pretty good. Oh, wait a minute. Oh, yeah, that's no good. Yeah, that's no good. I gotta clean that up. Now, I could increase the angle here. The angle of the dangle. Okay, let's try it. Okay, first let's try it without increasing the height. Now, how do I want to do this? Okay, I do have a fixed piece here that I can section. So I need to know what the diameter of this. Okay, the diameter is radius 4.2 smaller than or 8.4 smaller than 125. Right, let's try this. 125 minus 8.4. So it should be 116.6. put you on top. .116.6 by 116.6. Increase the number of sides. What are you doing? Come on. What the hell did you do that for? It's being a ghost now. Because I sure as hell didn't tell it to do that. Something's really making it lag. Jesus. Okay. You and you. Center. Freeze. You can move there. You can move there. Okay, that looks pretty good. Yeah, that looks good. Okay, let's create this ghost cylinder. Yeah, that looks good. How close is that? Yeah, that's almost dead on. Okay. All right. Let's push you through here. I can still select you if I need you. Okay. We still have the work plane here. So the base radius is 62.5. Nope. 0.5. With a height of increase the number of sides. Ow. You know what I can do? I can just get rid of the cylinder and just keep the threads. Why didn't I think of that before? Because it creates a mess like that. That's why. Okay. That's not going to work. The spiral's going to move. I was going to use a cone to make the angle steeper, but that's not going to work. What I need to do is use something like Fusion to make the threads. I need to create custom threads in something like Fusion. Okay, so let's write down our numbers. Our inner cylinder is 116.6 inner. And then the threads are going to be 3mm depth, thread depth. Which gives us 119.6. No, it's plus 6. Which is 122.6 and plus 2.4 gets us our wall thickness, gets us to 125. Okay. So we need a 3mm thread, a 3/6mm thread, depth with a 116.6 inner diameter, which gets us to 122.6 / 125 with 2.4 wall. Okay, so those are the dimensions that we have to get. And right now I'd like to be 40 millimeters tall. I'd like to be 42 millimeters tall. Just because that's the answer to life, the universe, and everything, right? How long do you dry PET G for? Ooh. The correct, okay, the easy way is overnight. The correct way is you weigh it. And when its mass stops changing, you've dried it enough. As you dehydrate the filament, you're going to be evacuating the water, which means the roll of filament is going to be getting lighter. So if you put that roll and your dryer on top of a high precision scale, you should be able to weigh it. And you're going to notice every hour that the weight is going to go down. It's going to get lighter. If you have to, pull the roll out and put it on a scale. But you might be able to just put your whole machine on the scale. And when the weight stops lowering, then you've gone far enough. Okay, so I guess the question is, can I still get into Fusion? Let's close Tinkercad since it's taking up a tremendous amount of resources. Let's close. If I'm going to do this much work on rockets, I might as well, I like Tinkercad because I like the interface of Tinkercad. But if I can make better threads, then I should do that. Wait a minute, thread maker. Maybe someone has a tool made for this. Matter Hacker's Thread Creator. Oh, it's something you have to pay for. Yeah, well, we're not going to do that. I want something that's free. I mean, that's not what I want. That looks like it's for adding threads to something. Wait a minute, you can make a thread in Tinkercad? No way. Oh, from an object. Well, I never thought of that. I never thought of going to Master Car and just downloading a threaded model. Let's see. 120 millimeters is about 4-inch. Although in theory, I can scale anything. That's 2.5-inch. And it looks like the biggest is M70, which is almost 3 inches. Okay. Let's do M70. Looks like I have to pick something. Where's the model? Well, don't that suck? This one doesn't have a model. A lot of these they used to, maybe they changed it, but you used to be able to download 3D models of files. Maybe you can't do that anymore? Well, poopy. What about M60? No. Uh, It'd be better if I generated a model. If I import a model and cut it, it's not going to be as clean. I'm assuming Tinkercad doesn't actually have a thread generator anywhere. I'm actually surprised they don't have some sort of generic like way to make a thread. That you would think that would be something that some people would want. Let's check out the models. Nope, nothing here. Let's see. Hardware. More. Ooh, what's this? Nope, that's a bung. 'Tis not what we want. That's a snap fit. Why would you show a picture of a nut and then not give any nuts? Isn't that funny? Hey, here's a picture of a nut, but that's the one thing you're not going to get. You're not going to get a nut. Oh, man. That's a flange tube. Okay. Newfound Drone Productions. How are you doing? OpenSCAD threads. OpenSCAD threads. Ooh. Not quite what I want. Oh, I bet. That's going to be fun. Well, that's why you pay for a model like that, to get all the ultra details. Vault Gen? Oh, for Rhino. Oh. Nut job on Thingiverse. Well, that's why you're paying for that. They put a tremendous amount of work into that. See, what I need is I need something that's polygonal based. Now that looks like a pretty clean polygon. In fact, that looks clean enough that it might be importable. Let's just grab a 25 by 8. Probably not live. The nature of places where we fly rockets tends to be the nature of places that don't have good broadband. Out in the middle of nowhere. We'll be flying out in the middle of nowhere about 20 or 30 minutes outside Alamosa, Colorado. So not likely to have much in the way. Well, I could, but then I'll be back to asking you to make something again when I want to do it again. So while I really do appreciate that, and if I get stuck, I'll definitely take you up on it, I want to try to come up with a solution myself. That is pretty clean. See, what I'm looking for is a model that is mostly polygons. So it's not like crazy, stupid, complex. Which, as you know, causes problems. So we want to be about 3 threads. I know. I just don't feel like wasting a half an hour of your guys' time as I download and install Fusion 360 and then get it running and okay. So I need to make a, we already know how big we need it to be. We need to be 116.6 by 116.6. What are you doing again? Why do you keep doing this crap? I don't even know how to get you back now. Because you went all AWOL on me. I must have done something. Probably made it 12,000 millimeters wide accidentally. No, it's good. Okay. So the first thing we got to do is make this a whole lot bigger. Oh, wait a minute. Was this symmetrical? 8 by 8. It is now. If it wasn't before, it is now. 42 tall. Okay. So what I need to do is center these like this, and then I need to scale this until that inner circle is the same size as my drawn circle, which would be right about there. That's pretty close. Left to right looks good. So 155 by 155. 155 by 155. Okay. That gets us pretty darn close. Let's see if it centers again. Yes, it does. Except I have a feeling those threads are going to be a problem. Let's find out. We then need to go to 122.6 gets me my inner and outer wall. Yes, it does. 122. Let's go 0.5. Let's see what that looks like. That is not much thread. That is not much thread. Okay, that's our inner. Okay, now let's create our cylinder. Let's go 150. Nope, no, I can't do it here. I have to do it in here. The radius 75. So 150 minus 122.6 is a 27.4 wall thickness. Nope, divide by 2. 13.7. Oh. If you had headphones, rest in peace. Sorry for your ears. That had to hurt. Okay. Alrighty. Let's center them. Wow, it's still too big. Or not big enough, I mean. But I know how to fix that. Okay. That does not leave me with much thread. What? What the hell did that? It's not centered anymore. Dumbass. Why do you keep deselecting? Why would you deselect? Why are you deselecting? Good. Keep making me mad. See what I do. I'll throw you out the window. Yeah, that's nowhere near. There's no threads there. So these threads are too close or too tight. So they go in, out, in, out. They're way too tight. Oh, wait a minute. I'm an idiot. This is very easy to fix. So first, let's join these two together. And then let's shove it out of the way. Okay. All I have to do is shrink this. Until I get the thread pitch I like. Bingo bango, baby. Get smart with me again, punk. Ah. Now what are you gonna do? Now what are you gonna do? Yeah. Let's see. We need to decrease the pitch a little bit. That's more like it. Let's see. Okay. Okay. I'm thinking I need a little bit less pitch still. All right, let's see what that does. Much better. Still a little on the rough side. But I think we're okay with that. Okay. Now let's get rid of some of the meat I don't need. Okay, Control D. Hmm. Okay. How big is this? 55. See you later, newfound drone. Oh, oh yeah, you gotta stay another 4 hours, buddy. Okay. Okay. Now let's chop off some junk we don't need. This is not perfect, but this is pretty clean. You have a great day, man. Do the best you can and work. Okay. It's still a little bubbly, bouncy. You know, it's not perfect, but all I care about is can I vase print it? Seriously? Hit that fucking button again. It's cold in here, so I got a heated blanket. At least my legs won't be cold. Okay. Let's see, I'm liking this so far. I just need to clean up this edge and clean up this edge. We already know how to do that. All right, I'm gonna wanna. Okay. Good. Control E. Wait a minute. Am I about to make this non-symmetrical? No, I think we're still symmetrical. Okay, so now I can use this to clean up that edge. Control E. And I can use it to clean up this edge. First, let's these two. That didn't do it. Yeah. Oh. Okay, that cleans up that edge. Now, can I rotate without breaking symmetry? Can. No, I think I broke symmetry. No longer even? Oh, it is. Should be good. Yeah, we're good. There. Clean threads. And are we still symmetrical? Yes. Okay. Let's export it. Make sure it exports clean. Bring it into Slicer. Make sure it slices clean. Hopefully at 0.3 millimeter layer height. Okay. All right. Get rid of the nasty one and bring in the pretty one. Are you going to work, my pretty? Oh, I don't like that. I gotta fix that too. I gotta chop that to here. I can fix that later though. Okay, that definitely prints very clean at 0.2. Okay, what about 0.3? It's close, but I think it's going to work. They look like a good solid overlap. The only way to really know is to try it. But it looks like I got to fix that. That is a glitch. I know what caused it. Okay. Same thing here. Okay. That looks good. I do have to chop this one back a little more. About here to make sure I get a good bevel. Although it'd be better if I the bottom cut. Okay, that's looking pretty good. Chop you a little bit, but I would rather. I might be able to extend that. That. Oh, I didn't get all the way down here. Yeah, that's no. takes care of that glitch. Now, can I get rid of a little bit more of this? Yes. Lower this there. That will give us our bottom edge. Okay. Go to just highlight this whole bulk. It'll be better if I do. Ow. I hit that. Better if I do it in stages. This, then this. Throw. We're a little over. We're at 58. I want it to be shorter. But I guess we could be okay with that. Make it 6 tall. I would have preferred shorter, but don't want to sacrifice too much in the way of strength. So, can I get away with just making it shorter? Try 50. Export. Let us try it again. All right, we have our solid bottom. We have a solid top, so we can transition. And that is looking pretty solid. Now, I have to actually print it. That looks pretty good to me, though. I'm liking it. All right. Let's make it, now I do need to shrink it a little bit. I need to take, 0.4 millimeters off of each dimension. The big one has to be the cut, but the actual thread has to be 0.4 smaller in both dimensions. This will need to be a 0.2 for both of these. You need tolerance for the threading. Although, will this thread enough? Wait a minute, I'm going to need this to be red. Is a straight block sufficient? Why do you keep doing that? Oh yeah, duh. Different program. I need to transition. There. Okay. Okay. Wait a minute. Both ends have to transition? No, only one end has to transition. Right? But it'll look prettier if both ends transition. There we go. That should be a curve, an arc, but I don't care. Hey. Are we still symmetrical? Yes. We are still symmetrical. Now I don't have to worry about this piece not being symmetrical anymore. Okay. Let's see. So I want this piece to be, well, we need to put a transition on both ends first. This 116.6 divided by 2, 58.3. So base of 8.3. Nope. Wrong. I'll get that again. And the top radius, we're going to make that 57 and 55. Sides. The height. 5. Okay. Should be able to center this. Good. Control P. U and U. Flip it. There. Down to 0. Okay, except this one's going to go outward. Base of top of 62.5. And I think that angle is acceptable. So that one will be 5. This one will be 10. Allow integration. Not perfect, but I think I know how to make it perfect. So I should be able to drop another cylinder in here. So 116.6511. Sides. Let's give it a bevel. First, let's change color. level. You make you a hair smaller. 0.5. Fully hide. That should be enough. What I'm trying to do now is make these parts merge into a solid, continuous part. Okay. How tall is you and you? 60. This needs. Why didn't you accept my input? Need input. Question. Original Ender 3 up and running, but after updating the Octoprint version on Raspberry Pi, the screen on Ender 3 on but blank. I can't print it a long time. Flash and display firmware. The Ender 3, I don't think the Ender 3 has separate display firmware. There are 2 plugs on the back of the screen, and I know you'll get a blank screen if you plug it into the wrong one. Did you try swapping plugs? See if that would do anything. All right. Let's see if that cleans it up. Yes! Look at that! Wow, it didn't just clean it up, it cleaned it up good. This is a little dirty on top here, but I'm okay with that. Actually, I know how to fix that too. Nine. Goodbye. Oh, yes. That is clean. This isn't perfect down here. This line shouldn't be here. That line should disappear. These lines are here because they're at an angle, but this line should have disappeared. But I think I'm okay with that. And I actually think I know how to fix. Oh, interesting. I don't do a whole lot with firmware. I don't think the Ender 3 has separate firmware. It's just part of the regular firmware. You may have just selected the wrong firmware when you compiled in Marlin. I know if you pick the wrong one, then it's not going to drive the screen properly because there are different screens available, Ender 2, R10, etc. So you may have just picked you may have commented out the wrong screen when you compiled. I mean, that would be my first guess. This is really clean, so I think I'm going to try to go for that little bit of perfection. Neither do I. I guess the first thing I would do is go back to stock firmware, verify the screen works properly, and then reattempt to integrate the Pi. That's the first thing I would do. Go back to stock, and try to reintegrate the pie. Once you get the screen working stock, make sure you didn't fry nothing. Oh, this is looking really freaking clean. Okay, so split it apart again. Now, if I remember right, this is 116.7. So I need to create a torus. And I need to add an even number to 116.7. So I could make it 117.1. But I can't split 117.1 evenly. I think I better leave good enough alone. I think that's about as clean as it's going to be. Because if I muck it up, I could just make it worse. So I'm going to leave this one as an object to play with. Then I can leave one broken apart so I can see the individual parts. And can I join this to this? Then join these together and still have it work? Yes. That didn't break it. Yeah, this one's perfect. There's no issue with the overlap. Here, there's an issue with the overlap. It's a very slight issue right on this edge here. Actually, you can see it. See how the edges don't quite line up properly? Oh, I know why. Because I made this bigger and didn't make that bigger. This is 122.5. This also needs to be 122.5. No, wait a minute. Again, there. This. 116.7. This needs to be 116.7. 116.7 by 116. Duh. That's why it didn't line up. You, join. There we go. Oh, fully manifold. That's what I want to see. Oh, yeah. Now I'm a happy critter. Turn you into a gray. Delete you. Control D. I don't care. Yeah, it's okay. It's okay. It's okay. I know, but I'm on a stream, so don't worry. It's okay. Yeah, we gotta talk about that later too. You gotta be careful how you're using the toilet. You broke it. Probably wiggle around too much when you're on the toilet. You gotta not move around when you're sitting on it, because we have a leak underneath it now. Not a huge deal. Just we gotta be careful. We're big people, so when we wiggle around, things break. Okay. And now I can adjust these transitions if I have to. Okay. So, how do I want to scale this now? I want to make this 0.1 taller. By 0.2 taller. Then I want to make it 0.2 bigger. So 0.4. 125. 4 by 125. 4. Okay. So this will be the printed one. This will be the cutting tool. So this is the tool I'll use to cut the one part, and then I print this part to fit inside this part. So that's a 0.2 millimeter tolerance on both sides with a 0.2 millimeter lift to fatten up the slots a little bit. Question is that enough? Only way to find out is to print it and try. All right, where are my tubes? Seg noses. I guess I can start with a seg nose. Grab one, copy you, go back into here. Oh, that's right. I gotta export this. I'm gonna keep this one. Well, I shouldn't have to. I shouldn't have to. This is clean. Damn clean. I should be able to keep all the parts. Okay, so split. Split. Hide you. Okay. Grab all this crap. We're gonna keep you because you're the right size. I want to keep inside too. I want to take all of you, but not get rid of. Gotta hide this. Huh? Oh, I still have to split that. Okay, that's fine. And just keep the tone. This I should be able to split. Hope that's not it either. Work. Okay. This is 120. It's not 125. That 115. Is damn close to our 116. In fact, we might as well make it that close. No, we have a bevel for a reason. We have a bevel for a reason. Okay. Go down by negative 0.1 millimeters. D. Turn you into a tool. Let's align it. Okay. So I should be able to join the tube first, then join this. Oh, that was wrong. Lifted, not dropped all the way down. 0. Do 390. Okay. Good. Now we should be able to merge this with this. There is our threads. And, oh, wait a minute. No, that's why we want the bottom. Don't want to completely remove bottom. Should be able to do that manually. This. There we go. I can just adjust it until I have my 2 perimeter border. There we go. That's what I want. Where's the entryway? There's the entryway. But will that permit entry? Can the part fit in there? Does that have to overlap the bevel? I don't actually know. I think that has to overlap the bevel. I think I need another bevel in here to allow an opening. I guess there's one way to find out. Okay. Let's try exporting and printing. Slicing, at least. Okay, get rid of you. Get you in here. Well, first of all, it's going to fail because I don't have a slot. At any point, do I lose my... Nope, I still have 2 walls. Boy, is that going to be one hell of an integrated structure. Wow. I don't even think I need ribs down there. The way that spiral moves around, always attaching to the wall. I don't think I need ribs until I reach the top of the threads. Hell yeah. Okay. That looks clean. Okay, so first things first, we have to slice it. But let's do the models first. Okay. So, I believe it's 122.6. Yes. I 0.01. Now we line them. There is the top of the thread. I should be able to this. Let's get this rotated. There. No, I want to thread it where it touches the wall. There. Bring that down until it touches right there. So we have congruence. How tall is that? That's going to become important later. 424. Two, 3, 8. 391. Needs to go one shorter. 7. Now this should be 391. 90. Yes. This is 7. $390 minus 7. So 53 millimeters. I have to lift up the first cut to be 53 millimeters. I can do that. Control D. Do a 22-degree pivot. And then duplicate that all the way around. Okay. And one of these has to be duplicated twice and shifted. That. I have to cut all the way through. 90. And 0. Okay. That's my inside-outside cut, my individual cuts. The individual cuts start at the top of the threads. Okay. Now, where is the other bits? Right there. I do want to keep that the same. Way I don't have to redesign the nose cone. But I do need to make sure we have enough room for threads. And we do. Okay. It should be as easy as that. Existing nose cone will fit. Existing shoulder will fit. There's probably a lip here, but it should be an angle. Yes, there's an angle. Okay. Okay. I think we got it. Okay. Try. No, I don't want to do that. Plus, the cleaner I can make these models, the less integration problems I'll have later. Less problems I'll have with Tinkercad throwing a fit. All right. Let us see if it successfully slices. I do not see any travels. I do not see any zits. I have 2 perimeters. I have 2 perimeters at the top. See if the marker moves. Nope, the marker is rock solid all the way down. And we have 2 perimeters on the down. Oh, this is nice. And it's lighter, 237 grams versus 251 grams. So not only did we make it lighter, we made it sleeker, and we knocked 54 grams, or I'm sorry, 14 grams off the weight. Now it's a half a pound. Means I can make 4 of these with one of the other ones, with 1 roll of filament. Okay. Now let me make sure we're not piercing the wall here. Looks clean. And we never go below 2 perimeters. No squish. See how it's not like disappearing into the other one, so it's not bulging it out. Yeah, that looks really freaking good. That is highly optimized. We'll have two. We maintain our two. Damn it, this is looking good. This is all at 0.3, so this will only take 7 hours and 40 minutes to print instead of 11 hours. No top or bottom layers required. All right. So this will become fixed, meaning I will not alter this. I'll just print the first, 60 millimeters. So, yeah, print like first 70 millimeters. Just print that. And, because then the next thing I have to do is start figuring out exactly how big this needs to be in order to fit. This is the exact size? Yes. This is the oversized. So this is the oversized. This one is 0.2 millimeters radius less. And it's also a hair shorter. Just a hair. So I got to print this as it is and see if works. Okay. Once I verify that works, then I can start integrating this component and this component into all my tubes. Now shrinking it becomes a lot easier. Now if I want to make this a custom length, separate, wrong one, separate, because I just changed this to 45. That's a difference of 145. Lower this by negative 145. That should be all I have to do. I should be able to now highlight this. No. I don't know why it thought it exceeded. Oh, that might be outside of bounds. I can shorten this. 5. No. No reason not to, really. No. No error. So there's the 245 millimeter tall one, and there is the 390 millimeter tall one. Then I have to make versions of this with this on top. But I can't do that until I figure out precisely what size this has to be printed so that it smoothly threads into this. Okay. I'm excited. Now I have clean, reproducible threads that will print at 0.3 millimeter layer height. And if I scale this up to a 0.8 millimeter nozzle, I could probably get away with a 0.4 millimeter height. Because a 0.6 is A 0.8 is 50% larger than, no, it's 30% larger than a 0.6. So I can increase the size of the part by 30% and maintain tolerances. So I could probably get away with the 40%. I can usually budge that about 10%. Still get away with it. Okay. The part. Okay. 4-inch seg nose, 90 millimeter. Okay, let's delete all this. Yeah. Okay. Now let's export this. Four-inch red. 4-inch red. So now what I'll do is in Simplify 3D, I'll just shrink it by 0.1 millimeters on each dimension until it fits. Then once I get the right dimension, I'll put that in Tinkercad. Go from there. All right. No welfare troll. He's okay. All right. But for anybody who wasn't here, because we're going to end the stream soon, finding 4-inch high power rocket. That is 99% 3D printed. The only part of this entire rocket that isn't 3D printed will be the paper tube that glues to here, the engine. Insulate the plastic from the heat of the engine. This unthreads. I'm printing another one right now. Change the size of motor you want to fly in the rocket. Swap the parts in, and that just threads right in there. Print out different tail ends. So here's 3 fins with like drop tanks and 4 fins of a more conventional like supersonic rocket. You can unthread and thread these parts together at will. Create whatever design you want, whatever shape you want. Threads tend to latch a little bit. Not bad, I guess. Unthread this one. Then thread in this one. Go. Now it's a 4-fin rocket. I can thread in a different one of these. I'm printing one right now with 3 29mm motors, so I can do a cluster, or I can go 38mm, go with a bigger motor. Add bays, like I added this section, add sections, take out sections, put avionics bays in here. Design a new part with the same basic structure. Create components to be able to whatever you want. I got 6 fins, 3 fins, 4 fins. I'm gonna do a 5-fin too, just because I like weird rockets like that. But the launch rod lugs are built into the design. I even went further. So I also put 1515 rail button. They're built in. They're all vase mode printed, and they are stupidly strong. So the rail is like, actually it's like the 3D printing rail, the extrusions that your 3D printer is made out of. Well, we use those rails to make launch rails for rockets. Rods can whip, while a rail is very stiff. You have a bigger, heavier rocket, you tend to want to use rails. So I have rail guides built in. I put 3 on here, strength, but I don't think I need. I think 2 would be plenty. I might get rid of that 3rd one just plastic, because these are way stronger than I was expecting them. That is really stiff. That ain't going. I'm going to get rid of one and just then what I might do is have the nose cone also have a little tiny rail button on the nose cone. Way when the rocket is on the rail and you have a really long rocket, nose cone can actually slot into the rail as well. Can't put it in the tube yet because there's no way to ensure they line up thread together. I'll have to practice with that and see if I can make that work. But the nose cone will turn. So I can line the one single rail button up. That will keep in from pushing on the rocket and bending the top half of the rocket away from the rail, which is going to put a lot of stress on these. If you have one up here also on the rail, then the whole thing gets pushed sideways and it can't bend. So that will greatly quite a bit. Go from there. But yeah, I'm very, very pleased with how this came out. Very lightweight. Well, compared to its size, it's very light. Obviously, the blow molded cone is lighter, but that's not that much heavier than a blow molded cone. It really isn't. And this has everything built in. Double wall thickness, built-in launch lug attachment points, higher shot cord. I did 4 for symmetry and for strength. So if you have an unusual powerful ejection or a heavy cone, you can attach to multiple points to spread the load. Yeah, this 100. Well, the nose cone is the only exception to vase mode printing. I can make a 100% vase mode nose cone, but this can't be a top like this. This would have to stop on double wall here. A single wall cone. Single cone all the way up to the top. Can do that. However, it'll be weak. Because instead of being a infill filled double wall tip, it'll be a single wall tip. It's 0.6 millimeter thick, but still a single wall tip. The cone tip is going to hit the ground first. So there's a pretty decent chance that tip would. So by switching to regular print mode, having infill and whatnot on top of the double wall cone makes that tip substantially stronger. Prone to be. I may try it just for the hell of it, but that only adds maybe a minute to the print time, maybe 2 print time. Can't add. I'll have to test it, but I bet you it only adds 1 or 2 minutes. We're only talking about 11 millimeters. Worth it for the strength increase. So that, but from here all the way down, it's 100% vase mode, no top or bottom layers. Just always make sure thickness down here is always 1.2 thick. So that's exactly perimeters that seal together without any gap or opening, without the need to construct the slicer, print top or bottom layer. This is coffee colored actually. It's from a company called 3DP. This is their coffee color. I'm impressed. I'm very pleased how it came out. I do wish Tinkercad would allow us to make more round shapes. This one is polygon facets. It's not bad, but I would like something more round. Well, Ray, if you're brave enough and daring enough, it could be. I wouldn't suggest it though, because that's gonna hurt. I mean, unless you can goats to 4 inches, that's gonna sting a little bit. Hey, hold still. Ignition. Yeah, you're definitely gonna feel that. Well, that's because the microphone's way over here and I'm hiding behind the rocket. This is pretty directional because it tries to filter out this surrounding noise. So when I'm directly in front of it, it works better. But yeah, this one came out great. I figured out how to integrate these tanks without creating holes or gaps or overhang issues. And one of the original problems I had was this angle here. The fin looks better when you have a steep angle here and a shallow angle here. It just looks better. It looks more rocket-like. But it creates a nasty problem. So this shape just looks better, but as you can see, it prints like crap because of the overhang. So what I did was I took the fin and I flipped it over so that this was the bottom, the much higher angle and prints better than this. But then it's a reversed crank fin and it doesn't look as the rear crank looks nicer than the forward crank. And then I realized they're both 1.2 millimeter circles on both ends. So instead of flipping the fin over, keep the fin at the normal angle and then just flip the whole part over and print it like that. And it worked perfectly. Look at that edge. That is as perfect an edge as you're ever going to get on a 3D print. I mean, that is just beautiful. No overhang droop, no issues whatsoever. I did the whole thing at 0.3 millimeters, except this part at 0.2. Now with the new threads, I'll be able to do the whole thing at 0.3 millimeters. But just beautiful, perfect edge. And then, of course, this is a very shallow angle, but because you're printing on top of another layer, you don't have that little bit sticking out on the end causing a problem. So you can get away with shallow angles when they're the top edge. You can't get away with it when they're the bottom edge. So instead of flipping the fin, I just flip the whole entire part and I print the part like that. Because it's vase mode, it works either direction. And because I have the same 1.2 millimeter footprint here as I do here, the only difference is the slightly smaller diameter, but the bed adhesion's the same. So now I just print them like this. Problem solved. So that's very cool. I want to do a ring fin. So I want to take this 3-fin design like this, and I want to shorten the fins to maybe make them that long, then have a little indent outside edge here, and then either 3D print or cut out from a cardboard tube a ring fin, lock it on there. So I just love ring fins. Ring fins are just freaking cool. Yeah, it came out great. And I lowered this one here. I was able to lower the mass by 140 grams, like 240, 247 grams or something like that. This is only 400 grams. I'm sorry, 540 something grams. This is almost exactly 400 grams. And that's after adding tanks and fins on the end, which I love that. So I am super, super stoked. This just came out so good. I'm so pleased with how it came out. Now I want to now I want to figure out how to do the whole thing, scale it. I want to make more scales of this. So for example, go down to like a 2.5 or 3-inch tube using a 0.4 millimeter. So a lot lighter duty, but still bigger than this. So bigger than this, but using a 0.4 nozzle so that it doesn't weigh, 4.5, 5 pounds for a whole rocket. And because I can still do the 400 millimeters tall, I'll still be able to make, a 3 or 4 foot rocket, but not be so ginormous. So I can make it a lot lighter. So now I want to do that for like all kinds of scales. And of course, I want to go bigger too. I want to do a 6-inch rocket. All of it. The whole rocket's recoverable. The only matter of fact, it's part of the safety code is you're not supposed to fly disposable rockets. The very nature of a disposable rocket's dangerous. No, this whole thing can be reflowed over and over and over again until something breaks. Obviously, if this comes down without a parachute, then that's going to be a problem. It's probably not going to survive that very well. But yes, this will have a parachute inside. Matter of fact, this will probably have 2 parachutes. I'm probably going to put a hook on the back here, tying a hook into it, so that I can attach a second parachute back here. Because if I bring it down horizontally, it'll hit the ground a lot more gently. Instead of, well, this one, I'd be better off hitting tail first. Because this one's going to have this big honking chunk of plastic in the back of it, and the fins are raked up, not sticking out. So it would actually be better to let this take the brunt of the force hitting the ground, because you could do that all day and you're not going to hurt this thing. So this one, I'll probably let this come down like that. Have the parachute up there. It's all threaded together, so you don't have to worry about it coming apart. Shot cord goes through those two holes there. Those two holes there, that's where the shot cord goes. You'll take your 1/4 inch, 1/8 inch Kevlar. It's going to need some pretty beefy Kevlar. You'll feed it down the hole, out the bottom, up the other hole, tie a slip knot. There you go, and then send your shot cord all the way up. This way, it's completely one of the few things. Something you don't see in rocketry very often is that these are serviceable. Not super serviceable, and you can't do much to service this. You can try to glue it back together, but it may or may not work very well. But if I break this, I can replace it. If I melt that, I can replace it. If I break a nose cone, I can replace it. If a body segment gets stepped on, the dog lays on it, he steps on it, I can just replace. I can pick an individual body segment and replace it. If I upgrade the design, somebody comes out with a new motor, and I want to fly that motor, well, no problem. I don't have to build a whole new rocket. I just take this in Tinkercad, take this exact part, and just put a different hole in there for the different size motor, and now I can upgrade this rocket with the new technology. And now it's a 29mm rocket, or a 38mm rocket, or a triple 29mm rocket. Well, that depends. My missiles don't go downrange very far, because if I think they're going to go downrange very far, I don't fly. I'm 400 pounds. If you think I'm going to make it a mile out and back, you're nuts. So I wait until that wind is nice and calm, or I use a long delay and some very big parachutes for a low altitude deploy. I don't like chasing rockets. But yeah, we have you can put your phone number on it, but usually where we fly, a rocket like this isn't going to drift that far. A couple miles at most. Get in your car, you drive out there and you get it, or somebody will have a quad, go out and get it, or a bike. And you usually just walk, because it's going to be like, a half a mile away. It's not going to be that far. If the rocket's going to go that far, you probably shouldn't have flown it. Now, as far as duration events where people are intentionally staying up as long as they can, we have tracking systems. You could put a G-spot in something like this. I can design one of these cylinders to be an avionics bay. I can put an altimeter in there and a beeper alarm in there. So you ever see one of those emergency alarms? You yank the cord. Take one of those. Well, we take those and we stick them in the rockets. We attach the cord to the inside of the frame and the buzzer to the parachute. So on the pad, it does nothing. And when the parachute comes out, it yanks out that pin and it starts making that warbling alarm. So if you land the thing in a cornfield, you can hear it. You can go find your rocket. We also tend to use, pink, blue, orange, yellow parachutes. So we can see them on the ground. We can send up a drone and go, oh, there's the 50-inch parachute all the way out there. They also have tracking systems, satellite tracking, and also cellular and radio tracking. Think fox hunt, ham radio, dog hound chasing. They do this with competition models. We're talking models like tiny models like this, and they have this it's called the Walston radio tracking system. It's this itty bitty little radio tracker that goes for like 10 hours or whatever. And you have one of those big Yagi style antennas, where you have the elements come out to the side and they get smaller. Looks like an arrow, and so it's directional. And you go out there and you hear, beep, beep, beep. Okay, it's that way, and you just keep going. And as you go further, you keep homing in on a line for it. And then we've even gotten pretty good with some of the old. If you remember the older days, it's a little harder with cell phones because the compasses are not good. If you calibrate your compass before you do it, it works pretty good. But the old GPS units, the old handheld, the Delorme units, Magellan units, the dedicated handheld GPS units before big smartphones became a thing. You can do what we call throw a line. So what you do is you would hold up your GPS and you'd keep aiming it at the rocket, aiming it at the rocket, aiming it at the rocket, and the compass is giving you a bearing heading, and it knows where you're at, right? And when the rocket hits the ground, you go tap and you draw a line. So on your GPS, it'll draw a line in the cardinal compass heading that you were aimed at from your standing position. So now you can actually go get in your car, drive around to about how far you think it was, bring up your GPS. It's not going to tell you where the rocket is, but it'll tell you where your line is. So you can go out to your line and start walking along that line, and you'll usually be within a couple 100 feet of the rocket. It's really pretty cool, some of the crap you can do with today's technology. It's like, you can do that? That's cool. And this was stuff 20 years old. We were doing this 20 years ago. I have to see if there's a line throwing app for cell phones. I bet you there is. I bet you there's one where it'll take a compass heading and you pop a line down and it draws a virtual line on your map, and then you just go out and you just walk it along that line using your GPS to stay on the line. And because if you know where you're at, you know exactly where you are. So if I have to walk, from here to here, well, if I'm standing here and the GPS knows within a couple of feet of where I'm at, and then it knows the compass heading I was pointed at, it can draw, like a ruler, it can draw a virtual line on the map that's along that compass heading that I threw a line. It's kind of like I take a fishing line and go all the way out past the rocket, and then you hold that line taut between that infinite endpoint and where you're at. Now you just walk along the line until you bump into the rocket. That is shockingly effective. If you have a good line of sight, we call it a line of sight. If you have a good line of sight on the rocket, you can throw a line using your GPS to give you a really good idea, especially if there's landmarks out there. Like if I see a competition rocket coming down in the distance and I'll hear people, anybody see it, anybody see it? I'll watch it until it hits the ground if I'm capable of it, because I don't have the greatest eyes. But if I got a line on it, I'll stand there and I'll point at that spot and I'll wait for that guy to come over to me. I was like, there's the line right there. Then, he'll usually either pick the marker or he'll use his GPS and throw a line out, and better than no chance of getting the rocket back. But these big ones very rarely leave the field. They're heavier. So, and I don't tend to fly crazy high. I flew my L2 rocket to 5,000 feet above ground level. So that's actually over 10,000 feet, because we were at 5,000, 6,000 feet station, out up in Colorado. But 5,000 feet above ground level, it landed 140 feet from the pad. I just walked over, picked it up, and walked back. That's the nice thing about the big ones. And then there's ways to improve your odds. So, for example, one of the things that I would do in a rocket like this is put an avionics bay on it. Will this even fit? It will. So, for example, I could put an avionics bay in here where there will actually be a section inside this tube, and I'll put what you call a dual deploy altimeter. So instead of having the nose cone separate, I'll have the entire rocket split in half. But the nose cone can also separate if I want, or just have it be two halves of this half. And what happens is there'll be two parachutes inside the rocket, and there will be two ejection charges. Won't even use the ejection charge from the motor. That'll just be plugged. And the altimeter, a little flight computer inside, will be connected to a pyro charge, and it'll literally blow off a little bit of black powder, poof, which will pressurize the rocket and blow off the end of the rocket. Now, what you'll do initially is you'll have the two halves of the rocket connected with a shock cord or a very tiny drogue parachute. Think like a little 8-inch parachute, like that big. For a 5-pound rocket, that's almost nothing. The idea is when the rocket detects apogee, when it gets to the highest point in the flight, it pops the rocket apart. Well, now the rocket is not coming down under parachute. It's unstable because it's broken in half, because you don't want the rocket coming in ballistic. Because that's, it'll hit 300 or 400 miles an hour on the way down, depending on how heavy the rocket is. So now the rocket's just going to tumble like litter, It's to be tumbling debris, which means it's not going to drift very far. It's going to come basically straight down because it's not really producing much drag for the wind to carry it away. And then that altimeter inside, it's not done yet. It's still working. It's going 5,000 feet, 4,800 feet, 4,500 feet, 4,000 feet. And then later on, 1,000 feet, 900 feet, 800 feet, 700 feet. All right, my trigger altitude is 600 feet. 600 feet. Fire the second pyro charge, which releases the laundry. The main parachutes then come out. And now my rocket is descending from 600 feet instead of descending from 5,000 feet. Now, of course, you descend from 5,000 feet under parachute, you're going to drift all the way out into New Mexico and Arizona. But if you pop your chutes out at 600 feet, well, it lands right there because it doesn't have time to drift. So that's what we call dual deploy. That's actually, I believe that's actually required for your level 3 certification. You can't use just a motor ejection. You have to use some form of electronic deployment. And so you do that with what's called a dual deploy altimeter. It's a little flight computer that knows how high it is above ground level. And apogee, it fires the first charge, which just deploys a drogue. Rocket plummets. And then when it gets to whatever altitude you define, 600 feet, 800 feet, 1,500 feet, you pick it. You program in what altitude you want it to deploy at. And when it reaches that altitude, it fires off the second charge, which deploys your main parachutes, and the whole rocket comes down nice and soft. So it's really quite cool, the things they can do. There's one thing that we do called TARC. It's the TARC, Team America Rocketry Challenge. If you ever have a chance to see one, go to one. It's amazing. It's basically high school kids flying rockets. And they have to fly to a certain altitude, and they have to stay in the air a certain time. There's requirements. It's kind of like a competition. I did not think model rockets were capable of being that predictable and reliable. I mean, we're talking, these nerds were down on the ground with their protractors measuring the angle of that launch rod with their anemometer, plug it into the laptop with the white kid. Okay, 14.5 degrees, 22 knots wind. And he's saying, oh no, we need 13 degrees. At this wind, it's going to drift too far. And they nail it every time. It's like, holy shit. We're talking, 100 teams, and they're all within a few feet of each other in accuracy. It's like, wow. If NAR competition rocketry were like that, they'd be screwed. Because those kids are good. Now, of course, those kids are flying one rocket, one mission, and they have the whole year to practice and figure out how to do that one mission. But still, it's amazing. It's part of our STEM outreach, STEAM outreach, science, technology, engineering, art, and mathematics. And, we're talking the White House comes out, generals from the Air Force come out, the EAA comes out. These are all the sponsors that help put on this event. Just for them, this is big money for the government and for the military and for our industrial engineering corporations. There's big money here because these people who participate in this stuff, they're the ones they're going to hire in 5 years when they come out of college as new engineers and chemists and biochemists and and mathematicians and physicists. These are the pool of people that are the future for these companies. And so it's pretty damn cool. I got to go to 2 of them. I didn't participate. I just went and took pictures. I helped run the range. You can see some of my time-lapse videos on YouTube. I had this great time-lapse video of the fog rolling into the field at the fairgrounds in Virginia. And then the fog getting burned off again. Very cool time-lapse video. It might be low again now because I'm probably too far away from it again. When I'm nice and close like this to the mic, you get some nice, good volume. But if I sit back a little too far, sometimes you lose a little bit. Am I still pinging yellow? Yeah, I'm still pinging yellow. Okay. But, yeah, it's incredible. These kids, these okay. You think I look smart? These kids make me look like a dummy. I mean, these kids are good. I mean, these kids know what they're doing. But I heard that. You know I bite, right? You know I enjoy biting, right? Yeah, she's getting bitten. Yeah, I bet you didn't, punk. But yeah, I'm this is turning out way better than I thought. I think people would actually do this, use this. So I want to try to see if I can get a hold of some of that lightweight foaming ASA and see just how light I can make this. I can compensate for strength by adding a few more ribs here and there to strengthen things. So add more ribs to strengthen up the structure a little bit. Um, Something, if Lightspeed's still around, something I'd like to try to figure out how to do. I'd like to figure out how to create a two-dimensional spiral. So right now, these ribs are just cuts straight up and down. You can actually see them on the end here. You can see like this rib doesn't actually pierce the outside. It pierces the inside. You can see it right there. And then it just touches the outside. And that's how I get my structural integrity. Oh, this is going to fly. Oh, yeah. This is definitely going to fly. Oh, ooh, I got to figure out how to pay for it. It's going to be about $80 to fly this one time. Well, I got to see how much it weighs. Some of the $40 motors might be strong enough to fly this. But I'm looking at about 5 pounds wet without the motor, 4.5, 5 pounds. That's going to take a pretty beefy motor. That's not a small motor. I already have a Cicerone case, so I could probably do a Cicerone relift. I think I already have a Cicerone 30 case. So I'll have to see what the load costs. But, yeah, between 40 and $80 per flight for a small motor. From my home, no. This I could not fly legally. Yeah, I wish, buddy. I wish I could afford that, but I've already got a 555. I got to get that set up because because the 555 would allow me to do some nice 6-inch rockets. Although at that point, you stop integrating the fins into the can, and you have a slot, then you glue the fin in. At that point, you start printing the fins separately, like I'm going to do with the ramjet. The fin will be printed separately. Yeah, I'm impressed. I'm very, very happy with it. Very pleased with how it came out. I'm blown away by how strong it is. It's way stronger than I thought it was going to be. But what I want to do is I want to take these 0-dimensional slots, basically, and I want to make them spiral. So I want a 12-slot helix, and that will give me 3-dimensional stability. So right now, this is incredibly strong, but between, you can still squish. So if you squeeze hard enough, you could break the skin there. If I had those cuts spiraling up the rocket, I can do a partial spiral, sort of. I could put a piece at an angle like this, and then just have a cylinder cut it on the inside and the outside. And that will give me a line that goes up this. And I could just rotate that then. There might be a way for me to kind of do that. Yeah, I'd have to do it twice. I would have to actually create a helix. It wouldn't be one big spiral. It'd actually be a helix. Huh. Wham Bam is irrelevant for first layer adhesion. Wham Bam has nothing whatsoever to do with first layer adhesion. Wham Bam is just a magnetic surface with a steel plate. Adhesion has to do with the sticker you put on the steel plate. And they offer many different kinds. They have PEI, they have PEX, and they have polycarbonate. So you can pick whichever material you prefer. Or if somebody else has a material you prefer, you buy their skid and you stick it on the steel plate. Unlike TH3D, his come with the PEI already attached, which is the only reason I don't suggest them too heavily. I don't prefer PEI. No, they don't put it on it. At least they shouldn't. They did it in the past. And I would specifically request they not put it on it. because I would want to put my own on it. Because I prefer the fuzzy, somewhat cloth-like surface. Just very, very good adhesion. And people say, it sticks too well. Who cares? You're going to flex it to get it off. Oh, comes pre-installed with PEX. I imagine they have extra steel plates that don't have anything installed on them. So the PEX is not bad. It actually worked pretty decent for ABS ASA. PEI was a little bit better for PLA. I never got around to trying PET-G, so I'm not sure about PET-G. PEX wasn't bad. My problem was it wore out over time. So eventually it wouldn't stick as well, and you'd have to refinish the surface. Very light, quad knot filing, down, just rough it up a little bit. Yeah, PLA, PET-G, you're probably going to you'd probably prefer the polycarbonate or the again, this was years ago, so the formulation may have changed, but I just preferred PEI over PEX. Very little difference in most cases. It might have just been psychosomatic. Might not have been much of a difference. But it works like PEI. Well, the only reason I'm getting into ABS ASA is because I need stuff that can handle temperature. I can't print this in a dark color. If I print this in a dark color and stick it on the launch pad, it's going to melt. Well, not melt, but it's going to start deforming. It's going to start warping. These surfaces are going to start caving in. Because it's all hollow. It's all vase mode. It's all single wall perimeter. So I'll probably end up painting this white. Just to reflect as much radiation as possible. Probably exactly what I'll probably paint it white. Maybe put little black stripes on it here and there just to make it more visible. But I'll probably paint it white, orange, and blue. Light blue, like neon blue, neon orange, white, khaki. I think even this coffee color is a little too dark for my taste. I'd be a little bit concerned about this absorbing too much sun. May in Colorado, probably fine. August, maybe not fine. Depends on how hard the sun is, how harsh the sun is. But yeah, I wanna do ASA first, see if that works. I can get away with open air ASA printing when I print thick, like with a 1mm nozzle. I don't know if a 0.6mm nozzle is wide enough. See, when you print wide, your overall stiction from layer to layer is increased, and so it's harder for the plastic to pull itself apart. So with a 1mm nozzle, with a 1.2, a 1.4mm nozzle, I can get away with open air ASA printing. This is an open air ASA print. I printed it on this printer right here, sitting on this table, in the summertime, of course. But that's a single wall perimeter ASA print, and it absolutely could actually print that. That piece printed in vase mode, just like that. Yep, there's cuts. You can see the cut right there on the bottom. To allow that to print in vase mode. That printed vase mode. Then this printed vase mode standing up like that. Yeah, put a couple ribs in there for strength. That's ASA. That's ASA. Parts just like that. So I upgraded his part to print in vase mode with 2 pieces. And because it's 1.2mm, pretty strong. But I don't know if 0.6 will be sufficient. There might not be enough layer bonding strength there to print open air, so I might have to put an enclosure around it. Oh, that'd be nice. Well, ASA is nice because it's a lot less warpy than ABS. But if you have to have an enclosure, might as well go with ABS because it's cheaper. But ASA does print very nice. Some of the smoothest prints I've ever gotten came out of ASA with a 1.4mm CHT nozzle. Matter of fact, my favorite nose cone, I used to make nose cones for sale before I did the vase mode stuff. My favorite nose cone was an ABS nose cone with a 1.2mm nozzle on an Ender 3. It's got to be the smoothest baby's bottom nose cone you'll ever touch. It's just the ABS just prints. When it doesn't give you warping trouble, ABS just prints nice. I mean, like, damn it, that's a nice print. PLA seems downright rough. compared to ABS. Oh, I bet it does. um, but well, my 500 is the CR10 S5, which basically has a 300 by 300 millimeter 12-volt hotbed. That's not going to warm up a room. I guess you got a Canovo or something similar on yours. One of those silicone heating pads. Probably is a heater in its own right. But yeah, this I'm thrilled with how well this is coming out. I mean, this I can release now, and I'm probably going to post some files. But first, I want to try new models. I can print both those test models in a couple of hours, so it won't take me long to rig up, get the tolerances correct, so that the parts will thread together. I also want to redo this with nubs. I want to maybe put little tiny fins on here, something that right now there's nothing for your fingers to grab. No grip. It's really hard to turn this. And once you get it going, you're good, but it tends to lock. So if I had little nubs on here, something your fingers could grip. Hang on, Sarah. But if it was something that your fingers could grip, it'd be a lot better. So I'm gonna add some. Yeah, I'm pleased with that. Very cool. Print a couple more body segments, see how wiggly it is at 7 foot long or something like that. And maybe I'll have to stick with this kind of a connector method just because it's stronger. Those might be too wobbly, thin. So see if I compromise strength with that. But that's it. 20 amps on the back. Wow. Yeah, that's a heater, buddy. That's a room heater. Wow. Yeah, I want to keep printing parts, keep coming up with more parts to make this modular system more complete. I got to order some tubes. I'm going to see if he can send me some cast-offs, like tube, because I got to get the dimensions right. All right, so that's it. It is 3:30 in the afternoon here. I'm going to call it quits for tonight. I'm just about finished printing that. Another hour, and the triple 29 millimeter motor mount will be done. And then I can, oh, then $30 will fly if I can get all three to light. Because you can get 29 millimeter motors a lot cheaper. It's it. I will keep you guys updated. I will start posting files once I confirm they're good. If you have any ideas, let me know. Don't forget to check out the links down below. When you use those links, most of those links are affiliate links. That is my primary source of income. I do not go work a 9-to-5 job. This is my job. That's what I do. You guys use those links, help me out. There's also coffee and PayPal links down below, Patreon link down below. PayPal's good for one-time support. Patreon's good for regular, continuous support. Think of this like PBS. I'm here with your guys' support. I will see you all later. And I'm definitely going to start working on more of 0.4 millimeter models, because more people can make those and more people can fly those. Working out well. I didn't think I was going to have this much fun making big giant rocket parts. So, you guys have a great weekend. I will see you next week.